So for those who already arrived, feel free to ask questions about last week's lecture and about the due date for submission of the in-class exercise. We have two dates. One is before midterm, the other is before final. So currently in Canvas, you cannot see that item yet. So it is set that will be available after some time, right? So do not need to worry about that. Just make sure that you write down some brief thinking or solution for those questions and put them in a big file. All right, and then when the submission becomes available, you can submit the whole file. Okay. Okay. So before we start the lecture, I'll ask one question in chat. About question 4 in tutorial 1, we are finding an optimal solution, okay, not approximate one. Well, actually by that, now of course, if you find some approximate one, you can show approximation ratio, that's also fine, all right? Although tutorial 1 is supposed for lecture 1, not lecture 2. But well, since you already know about the approximation algorithm, of course, you can also do that, right? And then today we are starting from traveling salesman problem. Last time we have one question about whether that figure is correct, right? Now, actually, many of you know that it's not correct, right? So at that time, the figure is not correct. I added 2 edges. Actually, I changed something, okay? I changed something on the figure so that the new red tool you see in this picture is now a real traveling salesman problem solution, okay? It's a tool going through all the vertices, right? And going through every vertex exactly once, all right? Okay, now as we said last time, if we remove one edge from the tool, it becomes a so-called spanning tree. So actually it's a path going through, oh, again, cannot, let me see. It seems that sharing has some problem. Let me share again. So is it the case that whenever I make it, let's see. So if I make it full screen like this, you cannot see the slide. Now can you see if I share again? Okay, now, okay, good. Okay, so now you see that if I remove the edge 10, right, it's a path. And it's a path connecting all the vertices exactly once. And then it is a special case of the so-called minimum spanning tree because path is also a tree, right? And then now I'm not going through how to calculate the minimum spanning tree. You can just treat it as a black box, okay? So suppose we know how to compute a tree going through all the nodes, while at the same time, the total cost of the edges on the tree is the minimum possible, okay? So that can be done very easily. Now, since it's a special case, then we have some property for this solution, all right? Now let's see, we have one property saying that the TSP is larger than or equal to MST, minimum spanning tree, all right? Okay, now on the other hand, we can do a TSP tour by the solution of minimum spanning tree. So the way is the following. So suppose you have a spanning tree like this. Altogether, you have 7 vertices, all right? And then what you can do is I number them according to my visit. For example, I start from 1, and then I go to 2, and then let me show the lace pen, okay? So I go from 1 to 2, and then back, and then to 3 to 4, and then like this, right? So I just do a so-called depth first search, all right, of the nodes. And then at some time, you will come back to the earlier nodes. And sometime if you can go, for example, as deep as you can, then you can still go on. For example, when you start from 1 and then go to 2, come back, and then go to 3, you go to 4, you can continue going deeper. But when you go to 4, there's nothing beyond that. So you have to come back to 3 again. But when you come back to 3, you can go to 5 now, right? Okay, you can go to 5 now, and then back. So basically, you are able to find a tour which goes through every edge exactly once, right? So this is what you can do. Okay, and then how about this solution? Well, actually this solution can be further simplified. Well, for example, you say, okay, I have from 1 to 6 and then to 7 and back to 6 and back to 1. But actually it's not needed because you can simply say, from 7, I directly go to 1 because directly going to 1 will be faster than going back to 6 and then to 1. So that gives you the tour here, right? So there are some shortcuts, for example, from 7 to 1, right? Okay, and then some other things like from 4 to 5, you don't need to go back to 3 and to 5. You can go from 4 to 5 directly. Now, by doing these shortcuts, you make the path or the tour even shorter, right? Because of the triangle inequality, this kind of shortcut is always faster or shorter compared to the original path, right? Okay. Now, so now you see, okay, actually, if we have the OPT being the cost of the optimal TSP tour, and then you have MST representing the total length of the minimum spanning tree, and the algorithm is this algorithm, right? The algorithm gave you this, all right? And then algorithm will have a very good performance. How to prove it? Well, firstly, we know OPT, optimal TSP tour, is larger than or equal to MST. This is already shown in our previous page, right? Okay. How about next one? The next one is LG, right? Algorithm is less than or equal to 2 times MST. Why? Because we are doing the tour based on MST, right? Based on minimum spanning tree. Every edge I go through it twice, right? Back and forth twice. And then therefore, this tour, the dash tour, is at most 2 times MST. Now, because later on we do some shortcut, but shortcut only reduce the length. So it's still less than or equal to 2 times MST, right? Okay, with these two inequalities, it's very natural to prove that this kind of solution, well, will be at most what? So this algorithm is at most 2 times MST, and then eventually the solution you get for algorithm is at most 2 times OPT, right? So this part I will skip. It just explains the shortcut, right? Explain shortcut. Okay. So now let's move on to the general case where the triangle inequality does not hold. Then what can we do? Well, okay, so that probably is more challenging, right? Now we can still ask question, for example, do we have a 2 approximation still? Well, most likely not, all right? Or if not, then can we have log n approximation? So you see log n is already a very big number, all right? Can we do it? Well, don't know. Now, if log n cannot be done, can we do n approximation, which is even worse? Well, so let's bear in mind these 3 questions and let's explore. Now, actually the answer is, well, you cannot do anything, all right, unless P is equal to NP. Well, this is very strong, right? So it's a very strong negative results, right? Okay, so let's see. Here is a theorem. So the theorem says for any function fn that can be computed in polynomial time of n, there is no polynomial time fn approximation algorithm. Okay, so no matter what this fn is, as long as it is easy to compute, you cannot have this kind of approximation for TSP unless P is equal to NP. Okay, well, so let's see. So that brings up the question of hardness of approximation. In the earlier topics, what we talk about is we find an algorithm and then say, okay, this algorithm, we can prove it is pretty good, right? It is 2 approximation, it is a log n approximation, etc., etc. But on the other hand, if you want to show your algorithm is really good, for example, you say, okay, my algorithm, my greedy algorithm is log n approximation. Now, I can also show that the best you can do is also log n. Then you can show to other people that your algorithm is indeed the best, right? Because nobody else can do better than that. Okay, so negative results sometimes is not bad. It is helping you to prove your algorithm is already good enough, right? Okay, so that's the rationale behind. It's just like when we talk about P and NP. So you may say, I cannot find a polynomial time algorithm, all right? Okay, but in order to justify my the solution is good, I can show that actually this problem is NP hard, and therefore nobody now can derive any polynomial time algorithm. So my algorithm might be good, right? Okay, so that's the same philosophy. By using negative results, it can help you to prove your current solution is relatively good. All right. So now let's look at how hard it is to approximate the TSP solution. All right. Okay. So in order to prove that, we'll first introduce a related problem called Hamiltonian cycle problem. So what is this? So Hamiltonian cycle is you have a graph G, and then it asks you whether you can find a cycle which goes through each node exactly once. All right, like this. When you have this figure, you see, I have 6 nodes, right? So I can find a cycle like this. Go from here, and then go to this node, right? And then here, and then here, and then here, and then here, then here. Okay, you can only go along the edges that exist in the graph. All right. Okay. For some graphs, there may not be such a solution. So this is called Hamiltonian cycle problem. I give you a graph. Please decide whether there is a cycle which goes through every node exactly once. All right. Now, in this graph, of course, it's yes, right? Now, if you have another graph like this, then everyone knows the answer is no, because you see this node only has degree 1. So if you want to enter this node, there's no way to exit, right? So there's no way to go back and forth for this node. Therefore, for this graph, you don't have such a solution. All right. Okay. So this is a no instance. Now let's formally write down the definition here on the left. Okay, this is a Hamiltonian cycle problem, right? Just like if I give you this graph, you may find a Hamiltonian cycle like this. All right. Now, actually, there is another related problem called Hamiltonian path problem. So there's only one word difference. Instead of cycle, here is cycle, right? And here is path. So I want to find a path that visits every node exactly once. For example, if you have this, right? And then you can go from left and go through all the nodes here and finishing at the right. That is fine. Okay, you don't need to go back to the left. It's not necessary. Okay, so path is less challenging, right, compared to cycle. Okay. Well, so now there's one theorem. It says that actually both versions, Hamiltonian cycle and Hamiltonian path, they are NP complete. No matter your graph is directed or undirected. Okay, so this one you can treat it as a black box. All right, so no worry, this is already known. All right, you are not required to prove it. Okay, so let's see how to show the approximation ratio is really bad. All right, now of course before that we first show that that's TSP. For general metric, it is NP hard. All right, okay. Now how to prove it? Now here is the one exercise. All right, we'll go through. Now we'll reduce from the Hamiltonian cycle problem. All right, okay. So if I give you a graph G, which is an arbitrary undirected graph with n vertices like this, okay, and then I will construct a length function on this graph like this, okay. So the length function is defined on Kn. What is Kn? Kn is the special notation for complete graph with n nodes. All right. So in other words, if you give me a graph like this, I will make a complete graph, which means every pair of vertices, there's an edge connecting them. But in order to, well, fully encode the information you have for the original G, we need to give different lengths for different edges. For example, if you have an edge in graph G, then the weight will be 1. Okay, this weight is 1, right? If you don't have such an edge, this edge is not in the graph, so this edge will have a length 2. So length 2 means what? The length 2 means it is, well, not, the edge does not exist in the original graph, right? So the length is larger, right? Okay. Okay, so now let's see. What's the equivalence of these two graphs? So remember, in the original graph, we are talking about Hamiltonian cycle, right? Okay, so Hamiltonian cycle, if you have it in the original graph, then in the new graph, you will have a TSP of length exactly n. Why? Because you can have a Hamiltonian cycle, right, in the original graph, and then every edge in that cycle has length 1. So if you map it to the target here, then you are going through edge 1, edge weight 1 always, right? You can find a tool which always goes through edge with length 1, and that will give you a total length of n, right? Now, on the other hand, if the original graph does not have Hamiltonian cycle, then it's not possible to find a length n, TSP, in the new graph. Okay. Well, so I will pause for a moment because this mapping is critical for the understanding of further slides. So I'm going to post the survey now. Okay, so did you get the correspondence between Hamiltonian cycle for the original graph and the TSP solution with length n in the new graph? Yeah, so such method can help to determine whether G has Hamiltonian cycle. You're right. So let me just see how many of you have understood the connection between the existence of Hamiltonian cycle in the original graph and the existence of length n, TSP, in the new graph. Now I see some of you still didn't get it. So do you have some specific questions about the difficulty of understanding this mapping? So I would like to address that. So you may send me private messages. Now remember, TSP is also a tool, also a cycle. Remember, TSP, traveling salesman problem, is also a cycle, right? It's also a cycle going through all the nodes, right? Okay, like this. And then you can see that a Hamiltonian cycle maps down to the target graph in such a way that every edge has a length 1, right? Because, well, if the edge exists in the original graph, then the length is 1, right? So your Hamiltonian cycle exactly corresponds to a solution where every edge has a length 1. So that means if you have a solution of Hamiltonian cycle, then definitely you have a solution of TSP with length n, which is the best possible, right? Okay. Now, you can also map it back. You say, okay, if I can find a solution for TSP with length n, that means every edge is 1, right? And then it could map back to the original instance, saying that in that instance, you have a Hamiltonian cycle, right? Yeah, so Ziao, you are right. Hamiltonian cycle, you can consider it to be a special case of TSP, right? Definitely, it's a special case. Yeah, yeah. So then the other one is also valid, right? So if you don't have Hamiltonian cycle in the original graph, then you cannot find TSP, right? So basically, there's no TSP. But on the other hand, you can add some connections with infinity weight, right? You say, okay, this edge is infinity, and then that means it will correspond to a TSP with cost infinity, right? And then there will be only 2 possible solutions. One is TSP with length n. The other is TSP with infinity length, right? Okay, so actually this already goes beyond what we are doing now. Actually, it's already several slides later, which is our final target. I will explain very soon. But for now, what I would like you to understand is the mapping between the solution of Hamiltonian cycle in the original graph and the TSP in this graph. So in this graph, you always have TSP. The only difference is the best TSP, right? The best solution for TSP is length is n or not n, right? If it's n, then it will map to Hamiltonian cycle in the original graph. If its length is not n, that means it is not possible to go only through those edge with weight 1, right? So that means somewhere, if you want to find a tour, you have to go through some place which has no edge originally, right? Like this. Okay, so that's the mapping between these 2 versions of the problem. Okay, so I hope that after my explanation, this we'll have more students getting the connection between them. So can I get a second round feedback? Now, did you get it, the correspondence? Oh, good. It's much better. Although there are still some of you who didn't get it, but definitely this time it's better, right? It is better. Now, of course, for those who still didn't get it, it's fine, because we are going to do a very obvious mapping a bit later, about 3 slides later. Okay, so let me finish the polling now. Okay, so now with this, right? So now we are proving this TSP is as hard as Hamiltonian cycle. If you can solve TSP, right? If you can solve TSP such that you know the minimum length, then I can immediately conclude your original graph, whether it has a Hamiltonian cycle, right? Because if my solution is n, then I can tell you, okay, your original graph has a Hamiltonian cycle. If my solution is larger than n, then I can tell you your original graph does not have a Hamiltonian cycle. Okay, so that's the one-to-one correspondence. All right, okay. So that gives us this one, right? Okay, so if you don't have the Hamiltonian cycle, then in your constructed instance, your TSP has a length at least n+1 because n is no longer reachable, right? Okay, but now comes a very important point. So is this 2 very critical here? Because just now, when we construct the graph, we say that if you don't have an edge, then I pretend you have an edge and its weight is larger, it's 2. But actually, we already mentioned one possibility that it can be some kind of infinity, right? It can be larger, not necessarily 2. Actually, no matter which number you put there, it will be the same. Yeah, so I see that some of you say that it just need to be larger than 1, right? You can, well, so that's very good news. Why? Because that could help us to prove the approximation lower bound. All right, so let's move on. Okay. So here, you see, how about we change it to something like n+1, then what's the result? Okay, so for n+1, then what do we have? I'll say, okay, if you have a Hamiltonian cycle, then the TSP has length n. Otherwise, TSP has to go through at least one edge whose weight is n+1, right? Not all edges are length 1. So you have to go through at least one such long edge. And if you add that long edge into your solution, your length will be at least 2n, right? Okay, will at least be 2n. So this is okay, right? So we have n+1, one edge at least, right? The other n-1 edges, each of them can be 1. So it will be this, right? Right? So plus together, it becomes 2n, right? Okay, so that means, well, you have a solution for Hamiltonian, then your TSP for the new graph is n. If you don't have a Hamiltonian cycle solution, then your TSP solution is at least 2n. That means what? That means if you can do approximation better than 2, then basically you already solved Hamiltonian cycle problem. Okay, so we replace this by n+1, right? And then remember approximation, right? The approximation is something like this: your solution compared to optimal solution. Okay, so suppose we have this 2 minus epsilon approximation for TSP. Then what can you conclude? You say, okay, I just run it on this Kn. All right. Now, if we obtain a TSP cycle with length larger than or equal to 2n, that means what? That means minimum TSP length is larger than n. Now, you see we're doing this, right? 2n divided by 2 minus epsilon, right? Okay, because we say that this 2n actually is such an approximation, right? It's 2 minus epsilon approximation. So your optimal solution must be larger than n, right? If optimal is n, then you are only 2 approximation. So optimal has to be larger than n in order for the approximation ratio to be less than 2, right? Okay, so that means as long as you obtain a length of TSP to be 2n at least, then your optimal is larger than n. Optimal larger than n means what? What does it mean by optimal, the minimum TSP larger than n? It means that in your TSP, you cannot only go through edges with length 1, right? You cannot only visit edge with length 1. You have to visit at least one edge with length n+1, which means the original graph does not have a Hamiltonian cycle, right? Okay. Right, so this is the logic, right? Okay, so if I successfully, if I solve the TSP in the target graph, I get a solution which is larger than or equal to 2n, which is at least 2n, right? And then I can conclude, okay, my optimal one must be larger than n. If my optimal one is larger than n, that means in the first graph, in the old graph, the Hamiltonian cycle does not exist, right? So this is my conclusion. Okay. Now, on the other hand, if your solution for TSP is within 2n, less than 2n, then it means what? It means I didn't even touch one edge with n plus 1, right? Because if you if as long as you touch one edge of length n plus 1, your length will be larger than or equal to 2n, right? So if your solution is better than 2n, that means I didn't touch any edge whose length is n plus 1. In other words, all the edges I touch are edges of this type. And that will give us a Hamiltonian cycle, right? Okay, so basically, by solving the TSP in the target graph with the approximation algorithm, remember, we are not doing exact algorithm. We are using an approximation algorithm. We use this approximation algorithm to solve TSP, and then we can conclude, okay, in the original graph, whether you have Hamiltonian cycle or not, right? Okay, so again, I would like to do some simple polling. So is it okay with this argument? Yes or no? So this time, it seems a bit challenging, right? Because the percentage of understanding is less than the first one, okay? Yeah, so let me complete finish the polling first to see what question you have. I see one question. Yeah, okay, yeah, 2 minus epsilon 1. Yeah, fully understand, okay? So basically, this is a proof by contradiction, right? So here we are using proof by contradiction. We say, okay, suppose you have a good approximation algorithm, then what can we do? All right, okay. Now, let me draw some figure to make the whole process a bit clearer, all right? Now, remember we have two graphs. You have a G and you have a Kn, right? And then on G, either you have Hamiltonian, this I use the Ham, okay? You have a Hamiltonian cycle, yes or no, right? Okay, either it's yes or no. Okay, now you see, well, if you have a Hamiltonian cycle, then in Kn, what's your TSP length? N, right? So this is so in Kn, we talk about TSP length, right? TSP length. And in G, we are talking about Hamiltonian, whether you have a Hamiltonian or not. So this is Hamiltonian, right? Okay, well, so you see very clearly that if your G has a yes answer for Hamiltonian, then in Kn, the new graph, your TSP should have length N. And then if your G does not have a Hamiltonian cycle, then your TSP in the new graph should be at least 2n, right? Because you have to go through at least one edge with weight n plus 1, right? Okay, so I just want to, sorry, bother you again. Let me poll again. So is this argument okay? Sorry, I should not quote it. So is this one okay? The mapping, okay? Is the mapping okay? Oh, good, very good, okay? So the mapping makes perfect sense, right? Great, okay. So the mapping makes perfect sense. Then what are we doing? We say, okay, because this is optimal value, right? This is OPT. These are all both OPT value. So now let's say we have an approximation. We have an approximation algorithm, approx, okay? Oh, actually, some of you just asked the question, why larger than 2n? So because if you don't have Hamiltonian cycle, then that means you cannot go through only edge with weight 1. You have to go through at least one edge with n plus 1 weight. This edge does not exist in G, okay? You have to somehow bypass or do some kind of shortcut in the original graph G to construct the cycle. Otherwise, it's not possible, all right? Okay. And the length of the edges, either they are 1 or n plus 1, okay? There are only two values now, right? So by pass will plus n, because you see, this is the edge weight in the new graph, which does not exist in the old graph. So by going through some edge which does not exist in the old graph is very costly, right? It's very costly. Okay. Okay, so I see some other questions, but yeah, for now, I guess I will just finish my explanation, and then everything will be clearer later on. Okay, now, so approximation algorithm is doing what? It's doing something like this. If your optimal is n, then if your approximation ratio is alpha, then you can get a value less than or equal to alpha times n. All right. So basically, approximation says I cannot get this exact value, but I can get some relatively good value. So for example, if my approximation ratio is 1.5, so let me just use one example. If my approximation ratio is 1.5, then the value I get is 1.5n. Okay, in other words, if your optimal is n, then the actual value obtained by the approximation algorithm is less than 1.5n. Okay, it's less than this. Okay, because of the approximation ratio definition, right? Okay, now if your value is larger than or equal to 2n, now you know approximation ratio, approximation algorithm, its output will not be better than 2n, right? So if your optimal is something like this, then the value you get will be at least 2n. Am I right? So we are using two different threads for approximation algorithm. On one hand, it says that for the optimal solution, if the optimal solution is small, then approximation algorithm will give you a relatively small value, right? Okay. Now, if the optimal value is large, then approximation algorithm will give you a solution which is also large, right? Because approximation algorithm, the output has to be at least OPT, right? It will never be better than OPT. So approximation will be at least OPT. Therefore, you see, in these two cases, the small case and large case, sorry, this is not this, okay? Small case and large case, the output by the approximation algorithm, they are well separated. Meaning, if your optimal is small, then the value computed by approximation algorithm is also small, all right, in the smaller range. If your optimal value is large, then the output by the algorithm, approximation algorithm, is also large. So basically, you can consider I have a line of solution. Okay, this is 0. Okay, and this is 2n. So it tells you if optimal is small, then approximation algorithm will only output value in this range. All right. If optimal is big, then the approximation algorithm will give you a solution in this range. Now, these ranges, these two ranges, they are well separated, right? Okay. In other words, if eventually you see a value here, you can conclude optimal is bad. All right. If you see a value here, you can conclude the optimal is good, right? So basically, you are able to differentiate between this yes and no, right? Because yes and no correspond to good and bad. Okay. All right. So up to now, I would like to ask again. Now, of course, there are some other questions in the chat I will answer a bit later. So does this make sense to you about how we use approximation algorithm to differentiate two cases? One case is good case. The other one is bad case. Okay, so I can just simply depend on the output of the approximation algorithm to judge whether it's a yes case or a no case. It's a good case or a bad case. All right. Okay, so I can see that it becomes much, much better this time. Very nice. And then actually, I believe that after I answer questions from the chat, it will be even better. Okay, so I will finish the polling now. Okay, so there are some questions. Yeah, one question is, as the cost of virtual edges can be arbitrary, can we show lower bound that is lower than 2? Okay, so actually it's not lower than 2, it's higher than 2. Okay, so this is CL's question. And then there's another question. What if the approximation method is bad? Oh, okay. Well, we'll see very soon, okay? If the approximation method is bad, then you need to change the edge weight to make the whole thing work. Because if it's bad, for example, approximation is 3, then using this one cannot derive any conflict, any contradiction. We have to make the edge weight even larger, all right? Yes, yeah, so Siri, you are right. You increase the length of E until it can still separate the two sets. Very nice, okay? So basically, we have the two possible ranges of output by the approximation algorithm. We need to make sure that for yes case, the range of the output, and for the no case, the range of output, they do not overlap. If they do not overlap, you can perfectly conclude, okay, as long as I see one value, I know which category you're talking about, right? So this is the philosophy behind the approximation lower bound, okay? Yeah. So Wing Zhong, the question I didn't quite get, but I think that, well, after this explanation, maybe, well, one slide further, you probably can know the connection, okay, about the how to use approximation algorithm to differentiate the two solution classes. One is you have a Hamiltonian cycle. The other is you don't have, okay? Well, so let me move on. All right, so I believe that now the question will become minor. All right. Okay. So this one we already said, right? So basically, using these two classes of output, you are able to differentiate whether you have a Hamiltonian cycle or not. And then that tells us, oh, actually, your assumption is wrong, right? Because we assume you have a good approximation. But if you have a good approximation, we are able to separate these two things very easily. And giving a polynomial time algorithm for Hamiltonian cycle, that's a contradiction. So you cannot have such a good approximation, right? Your approximation cannot be better than this. Okay, so now let's prove the final result. Okay, so we show that actually, no matter which function you have, you cannot achieve that. Why? Well, we just create edge weights like this. We just make the weight of the edges which do not exist in the original graph be arbitrarily large. Okay, now the value we have is n times fn minus n plus 1. Okay, so I guess you already know the meaning why we have a minus n plus n minus 1 here. These are the normal edges, right? The edges with weight 1. Okay, so what's our correspondence? We say, okay, if you have a Hamiltonian cycle, then the TSP has a solution exactly n. If you don't have, then your TSP solution is at least this value plus n minus 1, which is nfn. Okay, right? Okay, so that's already a gap of fn, right? So n compared with nfn, right? It's already a ratio of fn. So basically, you are not able to achieve an approximation ratio better than fn, because if you can do it, then again, using the same argument, you are able to output two disjoint ranges, right, on two sides. The one side is yes, right? If you have a Hamiltonian cycle, then your length is less than n times fn. Well, on the other hand, right, if you do not have a Hamiltonian cycle, then you have a length very large, right? Larger than or equal to n times fn. All right. So, well, you can actually set this to infinity as we explained in the very beginning. If you set those edges which do not exist in the original graph to be infinity, then basically your TSP will be infinity if you don't have Hamiltonian, and will be a finite number, right? If you have a Hamiltonian cycle. And then no matter what function you multiply on this, it will always be less than equal to infinity, right? Yeah, okay, so Xinran, you are right. You can just consider LE to be a penalty function. And with this penalty function, you can achieve that. Well, the solution for the case when you have Hamiltonian cycle is a finite number, is a n, right? And then the solution for those graphs which do not have Hamiltonian cycle, the cost is infinity. Okay, so basically, if you have a approximation ratio, a finite approximation ratio, okay, and then that means, okay, I can differentiate the two cases. One is finite, okay, this value is finite, right? And this one's infinity. Oh, basically you are able to differentiate the yes case and no case for the Hamiltonian cycle problem in the original graph. All right. Okay, so that completes the proof. Well, so I hope that after this detailed explanation, you will have some feeling about how to show some problem cannot have good approximation, because we can use the good approximation to differentiate the original yes and no cases very easily, right? And then you're able to solve an already known NP-hard problem, but that's not possible. Therefore, for your new problem, it's also not possible to have this good approximation. Okay. Right. Okay. So then we'll summarize this topic a bit. Now, we have talked about the different algorithm design techniques. For example, greedy for set cover problem, you can get log n approximation, right? And dynamic programming for knapsack problem can give you a PTAS, right? And then we can also use linear programming plus rounding to solve problems like vertex cover. Remember the half, right? No matter whenever it's at least half, you round up to to 1, right? Otherwise, you round down to 0. So that can using linear programming and the rounding, you can also get approximation algorithm, right? And then sometimes you can even use the structures or relationship with P problems to solve well, to give approximation for the metric TSP, which means the edges satisfy the triangle inequality, right? Okay, now, well, of course, you can also combine multiple algorithms to get good approximation. For example, knapsack. So do you still remember that? Now this is a, what do we mean by combination of multiple algorithms to solve knapsack? Anyone who remember? What's that combination? Oh, very good. Okay, so Ziao, you get bonus. Now, basically, it's a combination of greedy and the largest item, right? Okay, so you take the better of these two, it will give you a, well, 2 approximation, right? Okay, so this is from our last lecture. Okay. Now, of course, there are other approaches which we didn't discuss here. For example, you can also divide and conquer, or some kind of local search, or reductions, etc., etc. Now here, local search, usually local search corresponds to heuristics. You say, okay, I search for a better solution in my neighborhood, right? So this one, I believe many of you are very familiar with. But actually, local search, some of them can also be proved to generate a solution of a good quality, okay? So in other words, people may be able to prove that certain local search algorithm, they can give you, say, 2 approximation algorithm or some 1+e approximation algorithm, etc., etc. Okay, that's also possible, but they are more advanced. We'll not talk about it here. All right. Okay. Well, now there are some tips for this topic about approximation algorithm. So usually, how to solve a problem? Well, firstly, you need to understand the structures of your algorithm, right? And then you may say, can I? Well, so is this? So the structures is very clear. And then you also need to understand the difficulty of your algorithm, right? Okay, is it, well, it's not difficulty of your algorithm, it's your problem, right? Understand the difficulty of your problem. Is it NP complete or P? Okay. And then you will start with some common or familiar techniques and try to prove approximation ratio, right? On the other hand, you may explore what? You may say, oh, is this approximation ratio the best for your algorithm? Okay, so here you see we have one word, tight. So this tight, the meaning is what? The meaning is, well, I have an algorithm. I can show it is 2 approximation. Now, is it possible that some other people show the same algorithm has a better approximation than I do? For example, I show this algorithm is log n approximation. Then other people using the same algorithm, they may be able to show, this algorithm is 2 approximation. Well, then your analysis seems to be not tight, okay? So you have to provide one example showing that, okay, using my algorithm, the ratio cannot be better than what I proved, okay? So this means the tightness of your analysis. Okay, this tight is for analysis. For the same algorithm, is your analysis the best? Okay, is your analysis tight? Did you try your best to prove the approximation ratio? Okay, so this is tightness of your analysis. Okay, now so in order to show tightness, then you only need to provide examples, right? You say, okay, there is one example where, well, the ratio is just this value, okay? Cannot be better. Well, that means your algorithm, well, you already exhausted its powerfulness, right? It exhausts its power. It's not possible to be even better. Now, of course, sometimes you may say, I want to disprove my conjecture. Well, can you still use examples? Actually, no. Now it's no longer feasible because you cannot say, oh, in this example, the ratio is good. Well, in this example, the ratio is very bad. Okay, in that example, the ratio is very good. Okay, so basically disprove your conjecture. It does not work by using examples. Okay, if you want to disprove, you have to prove a better ratio. Okay, well, then the other one, if your ratio, you cannot show it's tight, well, basically, you are not able to find a bad example which exactly give you this bad ratio, okay? And then you may try to improve your approximation, all right? You say, okay, can I give a better solution, right? Earlier, I have a log n approximation. Now, can I have a half log n approximation, maybe, right? Okay, but if you fail to improve that, then probably you may find some hardness results, hardness of approximation. Okay, so this hardness of approximation is the one we are talking about for TSP. All right, so basically show that no algorithm, no polynomial time algorithm can give you a certain level of approximation. So if this certain level matches the performance of your algorithm, then it's pretty good. So this is tightness of approximation. Okay, so this tightness, so if you want to match, well, find a tight ratio, then here, this tightness is stronger than the tightness here, because this tightness just means your analysis is tight, okay? But here, we are trying to say the approximation ratio is tight, okay? You have a ratio log n, then I can show nobody can do better than log n approximation. Then your algorithm could be considered as best, right? Okay, so I guess I will just stop here for the topic. Any question? I guess it's also time to take a 5 minutes break before we get back. Okay. Yeah, feel free to ask questions in Zoom or via talking. Okay, so Senior asks, the general worst approximation ratio is 2. So actually, let me share the screen. We have some discussion about the arbitrary worst, arbitrary bad approximation ratio. So let me just repeat that slide once more. Yeah, so basically, when you look at this page, where we make the cost very big for those edges which do not exist in the original graph, all right? And then if you have this cost very big, then it means that the difference of the optimal solution for TSP in the normal case, in the good case, in the bad case, they will differ a lot, okay? So in the good case, the length is n. In the bad case, the length is n times fn, okay? So this is a very big number, okay? So now the argument is there is no polynomial time fn approximation, okay? So now actually to be accurate, it should be fn minus epsilon, so slightly smaller than fn. So if you have an approximation algorithm which have a ratio approaching fn, then as we did earlier, you are able to differentiate two cases, good case and bad case. Good case, if you multiply that ratio, it will be less than n times fn. And bad case is at least n times fn. So good case and bad case can be separated, right? And that means you can solve the original TS or the Hamiltonian cycle problem, right? Now, there's a contradiction. Therefore, you cannot have fn minus a small value, this approximation. And this fn can be arbitrarily large, right? Fn can be 1,000. It can be n squared. So no matter which function of n you fill in here, this kind of approximation ratio is not possible, right? So I hope I answer your question, Xinan. Okay, thank you. So Jiankwan asked on page 37. Okay, let me see. Page 37. Oh, okay. Very nice. You caught me on a typo. Very nice. Okay, it's not n minus 1. Very good. So it should be something like n plus 1. Sorry for my typo. And yeah, actually, catching typo will be good. Okay, so although I try to avoid any typo in my slides, but sometimes I may overlook. So you will get 1% bonus to get this fixed. Okay, so it should be n plus 1. Sorry about the typo. Yeah, thank you. Oh, okay. So Ziao asked if the minimum edge cost and maximum edge cost is fixed, there may be some heuristic with approximation ratio. Yeah, very good. This is a very good point. Okay, Ziao. Actually, sometimes approximation ratio can be dependent on the maximum edge weight over the minimum edge weight. Okay, so this you will see in quite some literature. All right, so yeah, you are right. So this, I just want to confirm you are right. If you have a bound on the maximum weight, then of course the ratio cannot be very bad, right? It will be bounded by the max over min, very likely. Okay, very nice. Okay, and then Xuezhen asked, is this paradigm the most used one for proving approximation hardness? Well, actually, this is also something I would like to comment at the beginning of the second hour. It's actually not, all right? This is only something which is easy to understand, all right? At least it's still within normal, well, people like us, within our understanding. But the most common one, they use a kind of reduction using so-called, well, let me see. Yeah, so usually the approximation hard, there is one branch of proof using the so-called PCP theorem, okay? Probabilistic checkable proof, okay? Well, that's, even I do not know, okay? I didn't manage to understand everything in PCP, But the good news is the PCP only used for proving the first problem, which is hard to approximate. But for other inapproximability results, you can also use reduction, just like NP hardness. You see, you can use reduction to prove, because this is NP hard. And then I can do a reduction to our problem. And so our problem is also NP hard. And then similarly, you can do things like this. Oh, because this problem is difficult to approximate. And then after I do some reduction, do some transformation, I have our problem. And then I can conclude, oh, okay, in our problem, it's also hard to approximate. Otherwise, there will be contradiction. Okay, so basically, just want to comment that inapproximability can also be proved using reduction, just like NP hardness. But there, in the inapproximability reduction, you need to be careful because you need to maintain the gap of this approximation ratio, okay? You need to show a more detailed mapping between the solution, especially between the approximate solution, because for NP hardness proof, you only need to map the optimal solution. But for the approximability, inapproximability, you need to map the approximate solution to see whether you can still separate the two cases, all right? So, but, well, that will be more advanced topic. It will not be covered in this course, but it's a very good point. Yeah, so any other questions? Yeah, thank you. So during this break, I guess, well, you are raising very, very meaningful, well, very useful questions. Thank you. Okay. Let me start the next one. Just want to make sure you can see the slide. Let me first show. So can you see this slide, ski rental problem? Okay, good, thank you. Okay, so up to now, what did we talk about? We talked about the approximation algorithm, right? So basically saying that, well, if our computation power is only polynomial, then what's the limit we can reach, right? How can we compute a solution which is close to the optimal solution, especially for hard problems, right? For NP hard problems, what's the approximate solution we can get? Now, in this new topic, we are going to talk about online algorithm. All right. Okay. So online algorithm is a different field which needs a different kind of mindset. Okay. So let me just give you one example first, and then try to capture the nature of the online algorithm. Okay. This problem is called ski rental problem. I believe some of you may have heard it, and also may have known the solution. But well, for completeness, we just start from the beginning. Okay, so imagine that now is winter time, all right, and then in some regions of the world there will be ski possibility, right? So you can ski on the mountain with which are covered by snow, right? Okay, so you would like to do some kind of skiing, but well, you need to make some decision about the ski the ski tools, all right? So in other words, should we buy the skis or should we rent them? So basically, well, because usually if you buy it, it will be very costly. If you rent it, it will be cheaper. But sometimes buying is worth it because well, it can be used for a long time, right? No limit. But if you rent every day you need to rent, you need to pay the rent cost. And if you rent for too many days, it will not be worthwhile, right? Okay, so then which one is better? And then it depends on how many days we are going to ski. But the question is, we do not know how many days we can ski. Usually it's the case that when you get up in the morning, you see, oh, the snow is still there, right? And then you can ski. Now, but you don't know what will happen tomorrow, right? Okay, so basically this skier will go to some trip with unknown duration, all right, with a group, all right? And then on each day, right, you need to choose whether you rent the ski or purchase it. And the renting, we say the cost is 1. And the purchasing, the cost is M. And this M is larger than 1, all right? And then, as I said, well, when you get up in the morning, and then you will know, okay, today I can still ski. right? Or, oh, maybe I can no longer ski today. And then if you can no longer ski today, then tomorrow also no longer, right? Because if the snow is snow already melts, then, well, you can just assume the trip is over, right? Okay, so basically at the beginning of every day, you will know whether you can ski on that day, all right? And if on some day you can no longer ski, then all the future days you cannot ski. This is a basic setting, all right? Okay, so I would like to see first whether this basic setting is clear. Is it clear? The problem setting. Okay, so although majority of you are clear, but still there are someone who are not clear. But well, thank you. I guess I will make it. I will make you understand by using some examples. All right. Okay. Now, there are also some other assumptions. All right. For example, if you already purchased the skis, then you can reuse them in any of the following days. All right. So this is also assumption. Now, if you didn't purchase, then on the next day you can choose to rent again or to purchase. All right. Now, as we said earlier, the skier does not know when the ski season will end, but his target is to spend as little money as possible. All right. Okay. Now, let's see. For the offline problem, all right, if you already know how long the entire trip will last, for example, say, okay, it will last for T days, then what's the optimal strategy? Now, actually, as I said, right, so the purpose is to spend as little money as possible, but you need to make sure that in the whole ski season, you are able to ski. You cannot say, oh, today when I get up, it can still allow me to ski, but because I do not want to spend more money, I just give up this day. Well, you cannot do that. So I believe that this causes some confusion in some of you. All right. So basically, as long as the season is still there, right? As long as it is still possible to ski, you cannot choose not to ski. You cannot say, I just stay at home. All right. You cannot do that. Okay. So now, is it clear about the goal? All right. About the goal, you want to minimize money, but you want every day you have decision whether to rent or buy. And then, well, you cannot choose to avoid or skip, right? So you have to ski as long as you have the chance, right? Okay, good. Now everyone understands. Very nice. Okay, so now you see the offline solution is very easy. Why? Because, you know, if your number of days, right? Well, let me see one question. Oh, okay, so you should ask a question. The skier can know whether the winter is end at the end of each day. Actually, to be more precise, it's at the beginning of each day. All right, not at the end. At the end, you don't know. But well, I guess it's the same. At the end and the beginning, it's the same. So basically, you can say that it's at the beginning of every day. He knows that. Okay. The winter season actually has finished yesterday. Okay, so you will know this kind of information. Yeah. So now, if you see that the number of days is small, then definitely you should only rent, right? Because if T is less than or equal to M, then you just rent every day. The cost is T, which is less than M, right? Less than or equal to M. Well, of course, that's best, right? Agree? Well, now on the other hand, if T is larger than M, then the best is just to buy, right? Do not bother to rent, just buy. Because anyway, you need to ski for T days, which is larger than M, right? And then if you do not buy, the cost of rent will be more than T if you rent every day. If you say, I rent on some days and then buy at another day, then the cost will also be larger than M, right? So you can see that it's very clear, right? If your duration of the season is small, then the best strategy is rent every day. And the duration is long. The best strategy is just buy on the first day, right? Okay, so this one is okay. Sorry to bother you again. Very nice. Okay, so okay, still someone is not okay. Well, Okay, well, I hope that well, you will know very soon why this is true. Okay, so basically, because every day you need to ski, so well, I guess the confusion comes from what strategy you may have. If you can only buy or rent for the whole period, then this solution is very clear, right? Now, because yes, the days is smaller, then you just rent every day, right? Do a whole rent, and then if your day is longer, you just buy once. Okay, because if you rent, it will be higher cost, right? But I understand your concern. We'll come to it very soon because that is about the possible strategies. All right. Okay. Now you know what's the optimal solution, right? This offline optimal solution. So Jiankun asks, is this random? Do not know the possibility. Well, wait for a moment. Okay. So I agree with you, right? Because now we assume you know the entire trip, right? But if you do not know, then it's a bit chaos, right? You do not know what to do, right? In our new setting. So let's see. All right. So the offline algorithm, as we said, it knows the entire input from the very beginning, from the moment when you call the algorithm, right? Okay. So how about online setting? So in online setting, the algorithm will operate interactively over time. So whenever a new day arrives, I will decide whether to buy or purchase or buy, right? Or buy or rent. And then you see that the input is given to the algorithm piece by piece, right? After one day, I'll give you one extra information, right? An extra piece of information. Another day, I give you another extra piece of information, all right? And then at each round, you have to make a decision, right? In our case, it's either rent or buy, right? Okay, and then the decisions you made earlier, it cannot be revoked. You cannot say, today I buy, today I buy. And then tomorrow, it's okay, it seems that buying is not worth it because the season already ends. So can I say, oh, yesterday, whoa, sorry. Can I say yesterday I do not buy, I rent? Well, you cannot do it, right? You cannot revoke your decision, all right? Otherwise, it will be the same as the offline problem, right? Okay. So now, let's see. This is the setting, right? Every day you need to make a decision, either rent or buy. And then you cannot change previous decisions, right? And then the setting is renting cost $1 per day and buying cost M dollars, right? And in total, you have T days, but you do not know what T is, right? Okay. Okay, so let's look at the first strategy. The first strategy says, I just buy. I do not care how long the period is. Is it good? Is this strategy good? No, actually, it's not good because you already can imagine that if you buy on the first day, then I can tell you, oh, actually the season is only one day. That's a nightmare, right? Because the optimal solution is just rent. Okay, optimal is 1, right? Because your season is one day, but the algorithm is M, right? Okay, so that's really bad, right? It's a ratio of M. It can be arbitrary. It's very bad, not arbitrary bad, but it's bad, right? Okay. So this strategy 1 is not good, right? It's not good. And then there is also another extreme. Another extreme says, I never buy, I just rent. Well, this can be even worse. Why? You see, if you have many days, right? Another extreme, many days, T is larger than M, then the optimal solution is just buy, right? Which is M. But your solution is what? Rent every day, right? What's the cost? It's T. And then, you know, for arbitrary large T, this algorithm is arbitrary bad. Now, this is even worse than the earlier one, right? Because earlier one, the ratio is M. Although M can be very large, but still it's an input, okay? But now this one, T is not input, okay? T is not input. And then, well, this T can be arbitrarily large, and then that makes the ratio T over M very, very bad. It can be as bad as possible, right? Okay, so these two strategies will not going to make it, right? It's not going to make it, all right? Okay, so let me just pause for a moment. So can you follow this strategy 1 and 2? Why they are bad? The ratio can be arbitrarily bad. Oh, good, thank you. Well, Yeah, so I'll stop the polling, although there's someone who still cannot get, but well, I think you will know it after we explain the third strategy, okay? Okay, so now we may think, can we somehow calculate a so-called approximation ratio, right? Because our algorithm will output a solution. Your optimal offline solution also has some value. And then I compare these two to see how good our solution is, right? Okay. Well, but actually, we do not call it approximation ratio. You will know very soon why. Now, the definition, so here we are not talking about approximation ratio. You see the title, we call it competitive ratio. So first, let's see the definition. Actually, the definition is very similar as approximation ratio. The only difference is now we are talking about a solution returned by your algorithm, your online algorithm, compared to the optimal offline solution, right? So this optimal knows everything, but this online algorithm does not know everything at the beginning. It can only make decision when it see a piece of information, right? And then the definition is very easy, right? It's just because it's a minimization objective, you want to minimize the cost. So you do algorithm output divided by optimal to see how good it can be, right? So because it's minimization, this value will be larger than or equal to 1. We try to take a max over all the instance, which means no matter which input you give me, the worst I will ever reach will not be too bad, okay? So the worst of such ratio over all the instances, it is called the competitive ratio, okay? Well, so as I said, there's a worst case guarantee, right? In the worst possible input, the algorithm is not doing very bad, okay? Well, so as I said, do we call it approximation ratio? Actually not, because here, efficiency is not a concern. In approximation algorithm, we say, because we can only use polynomial time algorithm, what we can do is limited. We cannot solve NP-hard problems now. So using polynomial time, the best we can do is to get a solution which is close to the optimal solution. But now, this efficiency is not a problem because, well, you can assume, well, I have a super strong power. I can do some black box computation. Okay, I give you any input, give me an output immediately. Okay, I can do things like this. But even this can happen. You cannot get the optimal solution because you don't have the full set of information. Therefore, this part, okay, the difference from your approximation rate, difference from your approximate solution and the optimal solution does not come from the limitation of computation. It comes from the limitation of information, right? Okay, so let's just review the two strategies we have. Buy on the first day, it's bad for very small t, right? Never buy, always rent is bad for big T, right? Okay, so what's the natural trade-off, or what's the natural next step to explore? What kind of solution would you adopt? Oh, okay, very good. So you can combine them, or you can rent for some day, or you first rent, then buy. Oh, very good. Okay, so this is the very natural flow you may go through, right? So always buy, always rent, no good. But only buy, no good. Okay, so how about we rent for some day and buy? All right. Okay, so we can. Let's see. Let's do one exercise. All right, so some warm up example. Now, but this example is not showing algorithm. Okay, this example is showing some bad ratio. Okay. Okay, I see very many interesting suggestions to n/2 and n/2. Yeah, so they're very already very close to our final solution. But before we present the solution, let's first see what's the best we can do. Okay, what's the best we can do? Because it may not be possible that we do a very good approximation. So let's simulate a bit. So this is a decision tree, something like a decision tree. It says, okay, on the first day, I ask you, will your algorithm buy or rent? You may say, okay, my algorithm will buy. Then I will tell you, okay, the season stops. All right. And then you see optimal solution is buy, right? So optimal solution is rent. But the algorithm is what? Buy. Okay. Now here M is equal to 2, right? So if you buy on the first day, then I immediately stop the season, only making it 1 day. And then optimal is just rent. Your algorithm buy it, right? So 2. So in this case, this ratio cannot be better than 2, right? Okay, it's already 2. It's not better than 2. Now if you rent, I'll say, and then I ask you, on your second day, would you buy or rent? And I say, okay, I buy. Well, if you buy, then again, I immediately stop the season. And then in this case, optimal will just buy once, but your algorithm is rent for 1 day and then buy, right? It'll be 3. So the ratio cannot be better than 1.5, right? Okay. Now, if you say, oh, on the second day, I also rent. Well, I ask you again, on the third day, will you rent or buy? Then again, 2 choices, right? If you buy, I say, okay, now I stop. All right. So as long as you make a buy decision, I stop. Okay. Because that will make the algorithm worse, right? Because, well, as long as you buy at this day, then optimal again will only be buying once, but your algorithm rent for 2 days and then buy, it will get a cost of 4, which is not good, right? So 4 over 2 is 2. So in this case, your ratio again cannot be better than 2. Now, on the last day, on this third day, even if you rent, I can make you very bad. I also stop. All right. In this case, optimal is again 2 because optimal just buy once, but your algorithm is what? Rent, rent, rent. It's 3. So in this case, the ratio is also 1.5. So with this toy example, you can see that you can never do better than a ratio of 1.5 because, well, you can imagine there is a bad guy, right? Based on your algorithm's output, he will decide whether I give you 1 more day or not, right? Okay, and then by looking through this whole tree, you can see that, well, the bad guy can always manipulate so that your algorithm cannot do better than 1.5 approximation, right? Okay, well, we'll come back to it later, and also we will come to an even stronger lower bound. Okay, this is only one toy example. Okay, so this is one claim, right? So we claim that the no deterministic algorithm has competitive ratio strictly smaller than 1.5. Actually, this is proved by this figure, right? By this figure. Okay, so now, again, just to remind, this hardness of approximation comes from lack of information, not from the lack of computation. All right, that's why it has a different name, competitive ratio. Okay, so let's see the strategy, right? So these 2 strategies, as we said, is not good, and many of you have suggested some mixed strategy, right? So what's mixed strategy? Well, we can buy after M days. All right, so you have some guess earlier, right? So actually M is the best we can do. So what do we mean by buy after M days? M is the cost of buy, right? Cost of purchase. So what's the strategy? The strategy says, okay, on day 1, I rent. Day 2, I also rent. Up to day M, I still rent. So up to now, I spent cost M. Then on day M plus 1, if I find that the season is still there, then I buy. Okay, and then up to now, my total cost is 2M, right? Okay, so is it good? So actually it's very good. Let's see. If your season is at most M, the days is also at most M, then this strategy is optimal, right? Because, well, in the optimal solution, you also rent every day, right? You will never buy, okay? It would be because buy will have a cost M, which is larger than your current cost, right? Because now if your time is T is less than or equal to M, then your algorithm only takes cost T, which is less than or equal to M, right? Less than M. So which is better, right? Better than buy. So optimal will also not buy. Optimal just rent. So in this case, optimal solution and your algorithm solution, they are the same, right? Okay, now what's the other extreme? The other extreme says it's larger than M. Well, if it's larger than M, we know optimal will just buy once. It will never rent. how about your output? Your output is rent for the first M days and then buy, right? So your cost is 2M. Okay, not bad. My cost is 2M. Your optimal is M. So what's my ratio? 2, right? Okay, so basically you already proved with this very simple algorithm, you can get a competitive ratio of 2. Yes, the worst case is 2 times OBT, right? That's what we discover, right? Okay, yeah, so now I would like to bother you again. So can you follow this analysis? Very nice. Okay, yeah, great. Okay, you see, well, that's very nice, right? Because by this simple mix, I buy after I rent for M days. This algorithm can give us 2 competitive solutions, right? 2 approximation, 2 OPT. That's super good. Okay. Now, that's the end of the positive results, right? Okay. Now, of course, I can skip the proof because this is just a repetition. All right, it's not much deal, not much new things here. Okay, so I'll skip the proof. Now, the next one. What's the next one? Do you think? We have shown that one algorithm can give us 2 approximation, right? So what's the next we should discuss about? Very good. Okay. 1.5, or is it tight? Yeah, so all these are correct, okay? So can we improve this ratio, right? Or if we cannot improve, then what? If we're gonna improve, then we try to prove lower bound, right? And actually, this algorithm, the ratio 2, is tight because we do have example where it is exactly 2, right? It's just when t is equal to m, right? Or m plus 1. If t is equal to m plus 1, it's very, very close to 2 or approaching 2, okay? Arbitrarily close to 2. Okay, now let's see. The question, as many of you have observed, is whether we can improve the ratio, right? But actually, no. There's no deterministic algorithm that can give you a competitive ratio strictly smaller than 2. Well, this is a bit harder to prove because earlier we show you one example, this example, but this example can only show nobody can do better than 1.5. It's not 2. Well, to prove 2, you may think, then probably it's very difficult because we already go to, well, 3 steps, right? So we only managed to do 1.5. So should we go further down to make it even larger? But if you make it further down, then maybe the tree will be too messy. But the good news is what? The good news is the proof is not so difficult. So basically, there is one important observation, and this will address some of the earlier concern. Okay, I remember at one time I asked you whether I understand the problem or not. Some of you picked no. Okay, so here basically is the point when we'll come back to that to address why we only need to focus on certain type of strategies. So basically, some of you may be unclear about what kind of strategy can be adopted. And there can be many, right? For example, I rent today, buy tomorrow, and then rent on the 3rd day. But basically, these things are not necessary, right? Okay, why? Because after you buy, you don't need to rent anymore because you can use your ski for free, right? Okay, so basically, we only need to consider strategies like buy after X days of rental. So that's the only thing you need to worry about. They will never mix, right? You will never see rent, buy, rent, buy. You will not do, you do not need to do this, right? You just need to rent. At some point, you buy. Oh, that's it. Okay, so these are all the strategies you need to worry about. Okay, so let's see. X, what should this X be? All right. Okay. So as we discussed, right, other type of algorithms, they can only be worse. So for this X value, right, for this X value, then how to argue? I say, okay, let's try, okay? let's try if x is less than or equal to m minus 1. Now, because in our solution, we choose x to be m, right? We rent for m days and then buy. So suppose we rent for less than m days. What will happen? Okay, if you are less than m days, then the bad guy, which is designing the online sequence for you, it will set t to be x plus 1. So basically, he will just stop the season right after you buy. Okay, so that's why he set t to be equal to x plus 1, so that on day x plus 1, you will buy, right? After you buy, he finished the season immediately. Okay, so in this case, what's the ratio? Well, in this case, optimal will be x plus 1. Optimal means you still rent for one more day, right? Optimal will still keep renting on this day, but you buy it. Okay, so optimal is x plus 1. And then your algorithm is x plus m. Very good. Yes, we are right. Okay, so the ratio is x plus m over x plus 1, right? Okay, nice. What's this value? It's larger than or equal to 1 plus m minus 1 over x plus 1, right? Okay. Okay. So what's this value? Oh, because x is less than or equal to m minus 1. So which means this is less than or equal to m, right? Okay, so it's equal to 2 minus 1 over m. Now, actually, it's not the equal, okay, because x is less than this, right? Right? So it will be larger than or equal to 2 minus 1 over m, which will approach to 2, right? Okay. Now, so basically, when you make x be equal to, so as Yuichi said, make x be equal to m minus 1, and this ratio will be the closest one to 2. Okay, if x is even smaller, it cannot be that bad, right? Okay. Well, so this is one case, right? How about case 2? Well, case 2 is x is larger than or equal to m. Now this category includes our solution, right? It contains our solution. So when x is larger than or equal to m, you know, again, I set t to be x plus 1, which means I just stop the season after you buy. All right. And in this case, optimal solution is m, right? It just buy once. And the algorithm solution is x plus m, because you rented for x days and then you buy on this day, right? So it will be x plus m over m, because x is at least m. So this value is at least 2, right? Okay. So basically, 2 minus m minus m 1 over m is the best ratio you can achieve for any algorithm. Now, because our algorithm already achieved ratio 2, it's pretty good, right? It's already pretty good. Okay. Yeah, so this is how you prove the best you can do is just 2 approximation. All right. Okay, so is this one okay about lower bound? Okay, nice. Still. There's still someone who didn't follow. Yeah, maybe we'll use the break time to address those problems if you still cannot follow. And let me just answer some questions in chat. So Sinan asked, in practical situation, m cannot be infinitely large. So you still can be better than 2 approximation. Yes, you're right. So there is a gap indeed, because m is input. M cannot be infinitely large. So there is a small gap here. Okay, a small gap here. Yeah, so for small m, you might get better ratio. But using this analysis, if you say for example, after m minus 1 days, I buy, you may not be able to achieve this because yeah, you may do some calculation. Maybe you can achieve. Okay, if you pick a day which is slightly less, it might still be fine. but you need to, well, at least need to address all the cases. All right. Oh, okay. Now, so Jiang asked a question. We consider worst case, but another thing is we are talking about no algorithm can do better than 2 approximation. Now, the algorithm is buy after X days of rental. So sometimes you have algorithm saying buy after, say, 3 days of rental. And then this could be better than 2 approximation. So there is some algorithm which can achieve ratio better than 2, probably. But in order to make it work, we cannot use this argument because this is only one possibility. This is the argument for lower bound, all right? This is not argument for upper bound. So if you say, how about my strategy? Buy after, say, 1 day. And then what's the ratio? Well, that one need to be calculated. And then Ian asked why this one is 1, 2 minus. Okay, so that's because x is less than or equal to m minus 1. So the whole thing here is larger than or equal to 1 plus m minus 1. So you replace x by m minus 1. It will become even smaller. And that will give you 2 minus 1 over m. The last. Yes, there's a typo. You're right. Okay. Let me just correct that for now. There's a typo here. Let me stop the sharing for now. Let me correct that. Okay. Discard. Let me come back again. Yeah, thank you. So these two indeed should be swapped. Yeah, thank you both for pointing out this typo. Okay, so yeah, I will not go deeper about the. Let me make it full screen. I will not go further to explain what will happen if you adopt a strategy like buy after 1 day, and yeah, so actually, buy after 1 day will be very bad, right? So buy after 1 day, then the season just stops after 1 day. Okay, so that value could be very bad. Okay, so actually, yeah, actually, if x is very small, this ratio will be super bad, right? You see that when, so basically, the smallest ratio you can achieve is when x is equal to m minus 1, right? Otherwise, if you have even smaller, then the ratio will be even bigger, right? Okay, so that also explains that probably renting for the first m minus 1 days and then buy, this will be the best. Okay, this would be the best algorithm for now. All right. Okay, so correct me if I'm wrong. All right, so basically now we say if you rent for m minus 1 days and then buy, this will give you the best ratio. Okay. Okay, now you see that we have mentioned a lot of times about this bad guy, right? So basically we can consider there is a so-called adversary, and this adversary will construct an input sequence so that your algorithm will always be making the wrong decision for every step, okay? So this is the goal of the adversary. And then this also how you prove that certain algorithm can never beat a certain competitive ratio. And you will see more such examples later on. Okay, so this is only the starting point. Now let's summarize the online algorithm bit. Now, in online algorithm, you are doing optimization without knowing the input in advance, okay? Because the input is released to you one by one. And then you are comparing your solution with the optimal offline algorithm, right? And we need to perform nearly as well as an optimal algorithm that knows the whole input in advance. Now, because the optimal offline algorithm has more power than our algorithm, so technically this gap in the performance is not because of the computation limit, right? Therefore, we do not call it the approximation factor. Instead, we call it competitive ratio, right? Okay. Now, of course, on the other hand, just like approximation ratio, we also hope the competitive ratio to be close to 1. All right, no matter whether it's greater or smaller than 1, we hope it to be close to 1. Because for minimization problem, it's larger than 1, but we hope to be close to 1. For maximization problem, the ratio is less than 1. Again, we want to make it close to 1. Okay. So now the last one is just a comment, right? So even if you have unlimited computation power, you still cannot achieve a competitive ratio of 1, right? Because it's simply because you don't know the full information, right? Okay, well, so that's the final remark on this page, all right? Because of the lack of information, you have a gap. It's not because you have a limited computational power, all right? Okay, so we have quite some online problems. Ski rental we have to talk about, and the next one we are talking about graph algorithms such as matching. Now, actually, it's just matching. And then we also do talk about a simple scheduling problem. And then there may be also other combinatorial problems, but we will not cover it in this course. And then there are also something called online secretary problem or profit inequality or Pandora's box, etc., etc. And these things have something to do with probability. And we'll cover the first two, secretary and profit inequality. Okay. And of course, there are many, many other domains which need the online algorithm, like online dispatching, or when you, just like, for example, you have some taxis, right? You have some orders of taxis, how to ask different taxi drivers to go to take different orders, right? So these are online decisions. Usually in reality, people need online algorithms more, right? Offline algorithm, they can only be used as a benchmark to compare with the performance of the online algorithm. But in reality, most of the algorithms used in practice, they will be online algorithms. So if you are able to prove, well, this online algorithm has a pretty good competitive ratio, then your algorithm will have an edge, right? Okay, so that's the purpose to learn online algorithms. Okay, so yeah, another more fancy word, ride sharing, right? So some group of people well, sharing a taxi, right? Or sharing a car in their trip. Okay, now online learning, or something called a multi-arm bandit problem. All right, so all these, well, I guess the last two, some of you may be more familiar with. Well, but again, due to time limit, we are not going to talk about many of the black entries. Okay, well, and these researchers will go to many top conferences in CS. There are many venues here. I believe that some of you may know some of them, but again, we are not going into detail about where they can go. Okay, well, so now it's our second topic in online algorithm. It's called online bipartite matching. Okay? So the problem again is very simple. It's matching. All right, we already know something about matching, but just a review. All right, so matching in an undirected graph is a set of edges without common vertices. Okay. So for example, if I give you such a graph, right? So you have an applicant on the left, jobs on the right. Every applicant, you can only map one applicant to one job. And then what can you do? Oh, you can do something like this, right? This is a matching, right? Then what's the maximum matching? Maximum matching that says that I want to find the maximum number of red edges, which form a matching. Okay, for example, here you assign 6 applicants to 6 jobs, right? So basically, it's the best you can do. It's also called perfect matching. But sometimes you may not be able to get 6. Maybe you can only get 5. Well, if 5 is the largest possible number, it's also fine, right? Okay, so that's the definition of matching. Okay, so what is online bipartite matching? Well, online bipartite matching says I have a bipartite graph. On the left is red vertices, on the right are green vertices, and all the edges, they only connect red and green. They do not connect something inside red or something inside green. There are no such edges, okay? Okay, and then now online means what? Online means at the beginning, you only know U2, all right? They are already known to you. They are offline vertices. For example, there are jobs. You have so many jobs to be allocated to applicants, but you don't have applicant yet. So what do? You say, okay, I start with the matching without any edge, all right? Because now there are no red vertices coming. So I just wait, okay? And then those vertices come, okay? U comes, and then say, okay, I have one applicant. He's suitable for these 3 jobs, all right? And I will do what? I will say, okay, I will add one of them, which means I allocate you to one of my jobs, the second job, the second green job, right? Okay, done. I allocated my first applicant, all right? And then another one, U prime arrives. You have one, you have also 3 suitable jobs for him. But unfortunately, second job is already taken by the first applicant. So you cannot take the second job. You can only take the third one or the fourth one, right? Okay. So the goal is what? Is to maximize the size of the final matching. You hope that you can match as many applicants as possible, right? To my jobs at hand. Okay. So this is the background. All right. So again, before I talk about any solution, are you clear about the formulation, the objective, the setting and objective? Very nice. Okay. I see majority of you get the point. Okay. Although some of you may have some problem, but majority have. It's okay. So I believe that if you still didn't get it, then we will have a better understanding if I give you a bit more steps about this process. Okay, so this will happen very soon. All right, and then again, because it's online algorithm, you cannot revoke your earlier decision. You cannot say, "Oh, I give it to a second job," and then when I see U prime, I told you, "Oh, please, I want to change your job to the first job so that I can map U prime to the second job." Well, this cannot be done. All right, you cannot revoke any of your previous decisions. Okay, so with this, I hope that for those who didn't understand earlier, now you will be clear about the setting. All right. Okay, so you see, we already used the real world scenarios to talk about the matching, right? Basically, it's a job application and jobs, right? And or something like Google or Microsoft online advertising, where you load the page and then it means that it's kind of you arrived, and then it will show you some advertisements, right? Which suits you best. Okay, so it's also kind of matching, but in that scenario, it's more complicated because he's showing you more than one pages, right? More than one advertisement. Okay. Now, yeah. So I think that we will start with a very simple greedy algorithm. Now, again, you see greedy. Well, greedy is very, very powerful. All right. So what's greedy? Greedy says, when a node arrives, I just take an arbitrary available edge UV, if there is any. Okay, well, this algorithm is too simple. It doesn't even have any greedy element in it, right? But still, it's a greedy, okay? But in our setting, there is no weight on the edges, so it's not so much greedy, right? Okay. Now, you just need to make sure that this V, right, is not in the matching you already have, all right? So one example, again, you have green nodes on the right. So red nodes come. So, okay, I give you any edge, right? And then the second one comes, only one edge. Well, because you cannot revoke your decision, basically this one you have to give up. I do not give him anything. All right. And third one, again, has 3 choices. I give him 1. And then there's another one coming in who can only be assigned to 4th job. Then he has to be sacrificed. Okay. And then 5th one, he has 2 candidate jobs. I give him 1. But again, another one comes in. He cannot get anything because that only possibility is allocated to the applicant arriving earlier, right? So in this case, you see the algorithm give you a solution of size 3, right? Okay, how about optimal? Optimal, they just match the first one to the first job, second one to the second job, and so on, right? Okay, yeah, very good. Jianpeng, you're right. It's optimal 6, so it will be 3/6, right? Okay, so the ratio is what? 0.5 competitive, right? And then it tells us that algorithm cannot do better than 0.5 competitive. Is it right? Can you prove that? Can you prove nobody can do better than 0.5 competitive using this kind of argument? Yes or no? Okay, the answer is no, right? I'm only giving one example, right? How can you prove that nobody can do better than 0.5? It can only say this greedy cannot be better than 0.5. Oh, actually, this comment is correct, right? The greedy cannot do better than 0.5, but it does not mean any algorithm cannot do better, cannot be better than 0.5, right? Competitive. Okay. Okay, so Xinran asks, because every edge you pick, there are at least 2 edges in future you cannot pick. Oh, okay, so actually it's not at least, it's at most. Yeah, we'll explain that part very soon. Yeah, it's a very good point. Yeah, okay, so here, maximum matching, it's a kind of maximization objective. Therefore, our competitive ratio is defined in the same way, but it's less than what? Less than 1, okay? Because optimal can always achieve the best, and your algorithm can achieve something weaker, right? So it will be at most 1. We try to maximize that value, right? Again, okay, yeah. So again, it's a worst case guarantee. And then, so there's one interesting thing, right? So which is observed by Xinran, right? So actually, when every vertex arrives, if your algorithm pick UV to be added in your matching, then it's true that it will waste at most 2 edges. Maybe in OPT, U is connected to another node on the right, V is connected to another node on the left. So basically, algorithm just give up 2 possible candidates in APT. Every 1 edge in algorithm will give up 2 edges in OPT. So basically, this is the some kind of the rationale behind the proof of 2. Okay. Right. So basically, well, the ratio here can be as good as 2, as 0.5. All right. Okay. Now the proof is very easy, right? So the edge you added UV, then all the edges with an endpoint equal to U or V cannot be added. So OPT is also matching. Then it has at most 1 edge with endpoint U and 1 edge with endpoint V, and only 2, right? So basically, your algorithm just break the possibility of 2 other edges. So your loss will never be more than 2. All right. Okay. So this is a theorem. All right. So the online Babata matching has a the greedy algorithm can give you a competitive ratio of 0.5. Okay. So actually, there are some proof steps, but I'm not going to go through it. The main rationale behind is that the one I just explained, right? So every edge in algorithm, I will charge it to the optimal solution. But the optimal solution, you only have 2 edges mapping back to this red edge, right? So 2 yellow map back to 1 red. So basically, you will never see another optimal edge that the algorithm didn't choose. That's not possible. Okay, so basically, whenever the algorithm see a node, all right, if the algorithm didn't choose the edge, So suppose the optimal solution, right? There is one edge in optimal solution where the algorithm didn't choose any of the two vertices, all right? Didn't choose it. Then you can see that when the algorithm comes here, he can see this edge, right? He can see this edge. Why does he not choose it? It can only be because he already choose this edge to another partner on the right. Then he does not choose it, right? Or this one is already occupied, so he does not choose it. So there was only two possibilities, right? So anyway, you will never have to worry about the optimal solutions edge has no connection to any of the red edge, any of this kind of red edge here, all right? So that will give you the ratio of 2, all right? Okay, so I will not go through the details. This is pretty easy. I will give you a 5 minutes break. If you can understand the argument, then we'll come to it again, okay? So 5 minutes break. Okay, it's a very good question. Where can you download chatbox record of Zoom? So chatbox records, it seems a bit difficult. I didn't manage to find out how to record the chatbox too. That's a bit challenging. But I will figure out. I hope that in the coming weeks, I'm able to record the chatbox. Okay, it's a bit messy because you know, chatbox has a private and public, right? So definitely I do not intend to record a private too. So yeah, maybe for now we just stick to the recording for now, all right? In order to provide, well, protect the privacy for some private questions. I don't know whether it is possible or not. It's a tough question for me. Over the 2 years, I didn't manage to record the chat. But whiteboard, the sharing, all the sharing can be recorded. This I know, but chat I do not know. And also, so you will notice that at least in the beginning part of this course, every week, all 3 hours will be explaining new things. But in later half of the semester, probably in some topics, it could be the case that we'll have 1 hour left for explaining exercises. Okay. Oh yeah, so Siri is suggesting a very good approach. Yeah, you can do it by yourself, okay? All the public messages, you should be able to capture it. That's totally possible. Yes, you're right. And copy paste, I don't know whether it's supported. It may need to be verified. Yeah, because in some of my Zoom meetings, I cannot copy and paste from Zoom to other editing tool. It seems to be the setting of the Zoom. Well, but this part I'm not quite sure. Okay, so let me just query again. All right. So is it okay about the 0.5 approximation ratio of the greedy algorithm for matching? Yeah, so I see some of the feedback. Actually, it's about 40% students who didn't get it. That's very natural because, well, I believe that some of you must be very rigorous in thinking. So the argument I give you is not very rigorous, I admit. Okay, so okay, so it's totally possible. Let me just go through it. briefly. So basically, we are doing a mapping, all right? A mapping from an edge in the algorithm chosen by the algorithm and the optimal solution. Okay, so basically, it's also called a charging argument. So what does it mean? It means that I pick one edge from the algorithm. So I pick one edge, which is chosen by the algorithm, online algorithm, and then define this FE to be the set of all edges in OPT that share a vertex with E. Okay, so just like if I pick this red one, then F is this, right? And optimal solution, these are F, right? Okay. So now you see, actually, the first one is very important. It says that for every edge in the OPT solution, there is some E such that E star is in FE. So which means every yellow edge has one red edge connecting to it, okay? Or having a common endpoint as it. So this is what I explained a bit earlier, right? So I should use another color actually. This is not red. So this is not red. This should be yellow. Let me use my pen. Color. Link color. Yeah, okay. So this one is orange or yellow, okay? So I'm proving by contradiction, okay? You say, okay, suppose there's one edge in optimal solution which does not connect to any red edge. In other words, there's no red edge here, all right? So there's no red edge here. Then I'm asking you, when my algorithm sees this node, okay? When the algorithm sees this node, what can he do? Now, firstly, we know the algorithm didn't pick the yellow edge because we said that it's in the optimal, but not in in online algorithm. So optimal, well, so your algorithm didn't pick this yellow edge, right? This one, it didn't pick. It also didn't pick any edge starting from this node, right? It didn't pick any edge starting from this node. Because if it picks, then this edge, right? If he picks this red edge, then this red edge has a common point as the yellow edge. So that means that this E star is in F. So this is E star, right? This is E star. And this is E, right? So if he picked any edge like this, the red edge here, then E star will be in FE because they share a common point, right? Common endpoint. Okay. So that means when this node comes, he didn't pick any edge for him. Well, but you see, I have so many edges, right? I have so many edges going out from this U, right? But I didn't pick them. Why? The only reason is they are not available, right? They are not available means what? Their endpoints are already picked by somebody else, right? Okay. So, for example, right? But oh, sorry. Actually, I want to correct myself. So the only possibility is that all of them are already occupied, right? Okay. So let's look at this red edge, the yellow edge. This yellow edge currently is available. So why you cannot pick it? Because this one is taken. I should change to red. Okay. Let me change to red. Because this is taken by the algorithm, right? Since if this one is also not taken by algorithm, then I should be able to pick the yellow edge, right? The greedy algorithm should be able to pick the yellow edge. He is not able to pick it because the right endpoint already has an edge going to another vertex picked by the greedy, right? But again, if this is true, then the optimal edge, the yellow edge, has a common point as this red edge, right? So it belongs to that FE, right? Maybe FE prime, right? So there you have an E prime. So if it's this case, then it will belong to FE prime. So that proves the claim, right? So for any edge in the optimal solution, it must be somehow has some connection to red edges. It cannot be possible that it has nothing to do with red edges, but it's not picked by your algorithm. That's not possible. All right. Now, of course, there may be more details, but I hope that after this explanation, it will be clearer on your side. Okay. Now let me finish the remaining argument. Okay, and then by the lemma, which is in the earlier page, right? Fe is less than or equal to 2, right? Because optimal has a matching, right? So if you fix one red edge, then there are only 2 yellow edges which share some common vertex as the red edge. Okay, you cannot have 3. You cannot have another yellow one here, because then it's not matching, right? Okay, so Fe is at most 2. And then you see optimal solution is less than or equal to this. So for all the edges in algorithm, you add up the Fe, right? One further thing, these Fe's will not disjoint. So so it's at most, right? So sometimes some yellow edges, they may be counted twice. For example, if the red one is here, then this will be counted twice, right? It'll be counted both here and here. But well, if I do a sum, then definitely it is an upper bound, right? Will not be more than that. So optimal will not be more than the summation of Fe. And then because Fe is at most 2, so it will not be more than this. And this is exactly 2 times the size of algorithm, right? So that's why we have the ratio 2 here, which becomes half below. All right. So is it better? So now do you know this too? Let me ask pose a question again, and then let me check the chat. The number of U2 larger than or equal to the number of U1. Oh, actually, here the number does not have any connection, right? U2 and U1, they can be of the same size. It's not about U2, U1. It's about the, let me see. Yeah, so we don't have this constraint. We don't have this constraint. Okay, so finish the polling. Although the percentage become better, but again, it's not that it's not reaching 100% yet. Okay, it's not. It's about 70 or 80%. But I think that you could get it after some review after the class about the argument here. All right. So I guess that for the interest of time, I may move on for the moment. But the message I would like to bring you is that the algorithm, so the main idea is whenever you pick a red edge, you sacrifice the possibility of 2 yellow edges. So you will roughly get half of what the optimal solution can get, because optimal solution can get these 2, but you only get this one. Okay, so this is the non-rigorous high-level idea. All right, so if you want to catch the idea of the rigorous proof, then you may need to spend a bit more time. All right, okay, especially proving this. Second one is easy. This is easy. This one is difficult. Okay, this is not so obvious. All right, every edge selected by optimal, it has to have some connection with some edge selected by algorithm. All right, every yellow edge need to share the same vertex as some red edge. All right, so this is the claim you need to prove. All right, okay. Yeah, so this is 0.5, right? And then let's see whether this is the best possible. Okay, can anyone do better than 0.5? Well, so now it's time for constructing examples. All right, so see here we are given 2 vertices on the right, and then the U1 comes, and then you say, okay, please tell me which vertex you map this V1 U1 to. Okay, so basically, well, you have some choices, right? Either you do not match, okay, do not match U1, or you match U1 V1, or you match U1, V2. Okay, these are the only three possibilities. So let's see. If you do not match, that's definitely bad. Why? Because then the algorithm just stops. Or the adversary just stops. It tells you, okay, there's one applicant. You do not match it, your performance is 0, and the optimal is 1. So it's infinity, right? You're infinitely worse, right? Okay, so definitely that's not good. So if you match this, then the adversary says, okay, you occupy this V1. So I'll give you this one. Okay, I give you a V2, U2, so that it can only be matched to V1. Then in that case, the optimal is what? 2 edges, right? U1, V2, U2, V1, right? But your algorithm only can match 1 edge. This is again exactly half, right? This is half. And then you say, okay, how about if I choose V2? Oh, same. Then I let U2 only connect to V2. So again, optimal is 2 edges, but you only matched 1 edge, right? It's again half. So no matter which choice you made, no difference. You can only achieve half. Okay. Well, so this one, can you follow? Okay, so this one is much better. All right. Now, still, there are some of you who cannot follow. Just remember, okay, we have an adversary. We have a bad guy, okay? So this bad guy will add edges in according to the decision you make by the algorithm, okay? So let's just go back a bit about this process, okay? So as we said, if you match U1 to some nodes on the right, then there are 2 choices. One is mapping to V1, the other is mapping to V2. So if you map to V1, then the bad guy says, okay, now I give you a new vertex, which can only be mapped to V1. But because you already take it, so this new one will be left unmatched, right? Now this one's similar, right? This one's similar because you match to V2. So I give you a bad guy. I give you a new vertex, which can only map to V2, but definitely cannot take it because if you take it, it's a non-matching, right? Okay, so in either case, you can only match 1 edge, right? You can only match 1 edge. But the optimal solution, you see, this is the optimal solution, right? You match this, you have 2 edges, right? And you match this, you have 2 edges. So the optimal is 2. Optimal is 2, right? Your algorithm is what? It's 1. So it is 0.5, only this much. Okay? Yeah. So can you follow now? Although there are only a small number of students who didn't understand, but I still hope that the majority can. That's good. Thank you. Okay, so yeah. Okay, thank you. Now, well, I noticed that there may be still 1 or 2 who didn't get, but I think that it should not be big trouble for you. It is manageable after some review. All right. Okay. So remember this. In order to prove the lower bound, okay, how good an algorithm can do, you need to construct examples. And in those examples, the adversary or the bad guy or the one who designed the online sequence is very powerful. He can observe what your algorithm do and then decide to add a certain kind of new input to your problem. Okay? So this will happen in any kind of lower bound analysis for online algorithms, all right? Including the 3rd topic we are going to introduce today called scheduling, all right? Okay, so I hope that by the time we finish scheduling, you will know better, at least for those who still didn't get the point here, all right? Okay. Yeah, so what is scheduling? Well, scheduling is something I worked on for some time. And well, the statement is not difficult. It tells you have a set of jobs, J from 1 to N, and you have a set of machines, M from 1 to M, okay? And then every job has a size, which is PJ, processing time, in other words, okay? And then each machine has a speed, S1, Si, okay? And then if a job is processed by machine I, J processed by machine I, it takes time, Pj over Si, which means if your job is processed on a fast machine, then the processing time needed is shorter, okay? Larger Si means shorter processing time, okay? Shorter time. Okay, and the schedule is to assign jobs to machines, all right? And then Li pi is the load of a machine I for schedule pi. And what's a load? Okay, load is all the jobs assigned to machine I, all the jobs assigned to machine I. So pi j equals I means the job j's machine is I, okay? Pi is a function. Pi maps jobs to machines, okay? So if j's machine is I, then I add up all these pj. I add them up, divide by the speed of the machine I. It will be my load. It means how much time machine I needs to finish all these jobs assigned to me, right? Okay. And then what's our goal? Our goal is to minimize C pi. This C code is called make span. Okay, it's a maximum load on all the machines. So it's a maximum, the largest value taken among all the machines L, among all the machines duration. Okay, how much time I spend on each machine, right? Doing jobs. Okay, so I will take the largest one. This is the make span. Okay, this is the make span. All right. Okay, so now, without giving further examples, I would like to know whether it's clear, the goal and the setting. Okay, good. Majority of you get it. Some of you didn't get, but I believe that after we explain the simple examples, especially the examples where S is the same for all the machines, you should be able to understand. Okay, so let's move on. Okay, so online problem says what? Says that jobs arrive one after another. All right, and after it arrives, it needs to be assigned right away to some machine. Okay, and the number of jobs or the size of future jobs, they will not be known to you until they arrive. Okay. All right, and then see one question. For online problem, all we can do is just to make the worst case not too bad. Yes, you're right. So Xinran, you're right. For online problems, you try to use some algorithms whose worst case is not too bad. Or in other words, it has a good competitive ratio. All right. Okay. But of course, on the other hand, you can also prove that nobody can do better than this, right? Whenever you propose an algorithm with a competitive ratio, say 2, you can at the same time try to show no online algorithm or no deterministic online algorithm can give a competitive ratio better than 2. And then it means your algorithm is best, right? It's the best possible. So that's the, well, final goal, right? So we are trying to show the algorithm designed by you is good. The second step is the best possible. Well, that will finish the story, right? Okay. So let's just start from a very easy case about all machines have speed 1. Okay. So when machine has speed 1, well, you only have processing time, right? You just add up processing times. Yes, very good. So Jianchong, you are asking a very good question. So in our setting, it's something like a fake online or some semi-online. What does it mean? Usually online says that when your time moves on. So I guess this also explains why somebody still didn't get meaning. Okay, so when the time moves on, you see more and more jobs, right? But that means you can only process those jobs after they arrive, right? Okay, or after some time. You cannot process them right away. Well, that's probably not so good. Okay, so here, we assume that the jobs will arrive any time. Oh, so will arrive at the beginning, 0. Okay, job will arrive at 0, but they have an order. Okay, So at time 0, all the jobs arrive, but they arrive in some order. And then whenever some job arrives, you have to allocate it immediately. But allocate does not mean execute. Okay, it does not mean you start doing jobs on the machine. It just means allocate. Okay, but in terms of make span, actually allocate and processing is the same. Now you will see very soon why this is the case. Okay, but at least you are raising a very good question. Okay, so we assume all jobs arrive before the machine begin to work, but these jobs arrive with a certain order, with a certain order, and then you have to follow the order of arriving to allocate jobs to the machines before they're executed. Okay, well, so maybe I'm not making myself very. So did I answer your question? Not quite. So maybe yeah, let me just explain the algorithm first, and then try to see whether it will have a better interpretation about what I just said. Okay. Now the algorithm is something like this. It's called least loaded algorithm. It's again a greedy algorithm. It will assign each job to the machine that has the smallest load. What does it mean? I mean that I have one job coming in, I assign to any machine because nobody has any work to do, right? A second job coming in, I assign it to machine 1. Why? Because machine 1 now has no load, right? Before you assign this job, it has no load. And machine 2 has already some load, right? And then I will assign second job to machine 2, to machine 1, sorry. And then how about third job? If I have third job coming in, which machine do I assign it to? First machine is top one, right? Second machine is bottom one. So if a third job comes in, which machine I assign to? Yeah, very good. You assign to top or first, right? Okay, like this, right? And then next job, which machine? Good, okay. And then next job here, right? And next job here, okay. Next job here. Okay, done. I allocated all the jobs, and then it will be there. This dashed line is their load, right? The first machine now has this much load, and second machine now has this much load, right? Okay. Yeah. So basically, you can imagine that I didn't start doing jobs yet, but then so the only process I'm doing is allocating jobs to machines, right? After the whole allocation finishes, I start executing all the jobs by individual machines. Okay. Okay, so I see some comment about J. Oh, very good. Thank you for catching up with the typo. You get the bonus. Okay. I will correct the slide a bit later. All right. Thank you. Okay. Yeah, so the typo noticed by some of you is this one. So this is a typo. It's not M, it's J. Okay. And we're talking about jobs, right? Jobs are not machines. It should be small j belong to capital J. Okay. Yeah, very nice. Okay. So now what are we going to do? Now in general, okay, so this is only in general. So in general, you have a job coming in. You just compare this L1, L2. If L2 is larger than L1, you assign it to L1, right? So this is the whole thing, the whole algorithm. And then you can also explain, so it also can also explain the one I try to make clear. All the jobs arrive at the beginning, but they have some order. And then you follow that order to assign jobs to machines. And then after you assign all the jobs, machines start doing things. And then their finishing time is the machine's load, right? Okay, so now let me trigger the questionnaire again. Now are you clear about the setting of the question and also the algorithm? Okay, so better than last time. That's nice. So I believe that after we analyze the ratio, it will be even more clearer. Okay, so let me stop the query. Okay, so now one thing to remind you, the adversary or the bad guy who designed the online sequence, it can select the worst instance. All right, no matter what number of jobs or sizes, as long as it can make your algorithm suffer, then he will do that. Okay. All right. Okay. Now, next one, we are trying to show this algorithm, this greedy algorithm actually is 2 minus 1 over m competitive. In other words, it's about 2 approximation. All right. Well, how to prove? Well, here, when we try to prove something, we usually need to find certain lower bound for optimal solution if the purpose is to minimize something. Okay, so let's write down the optimal schedule pi star. All right, so we have 2 lower bounds for the make span or the largest load on any machine in the optimal solution. Now, one lower bound is this. It's at least you add up all the processing time divided by m, which means you evenly distribute all the load to m machines. All right, so this value can never be larger than optimal because anyway, you need to finish all the jobs, right? You need to finish all the jobs. And the best you can do is to evenly distribute all the load to m machines. And that value is exactly this. So this is the best you can do on the condition that you can do some kind of fractional allocation, right? You can split jobs into 2 machines, okay? Even you can do this, you cannot do better than this load. Therefore, the optimum make span will be at least this total processing time over m. Yeah. Okay. Yeah, Xingran, you're right, right? So just imagine that I allow you to be more powerful. You can split jobs, and then the best you can do is still only summation of processing time over the number of machines, right? Evenly distribute, and therefore, well, your actual optimal can never beat this bound, right? Cannot be smaller than this because your optimal has even more restriction, right? Okay, it cannot split. All right, so then the longest one must be somehow larger than the average, right? Okay. Okay, so this is one bound. There is a second bound. The second bound, oh, sorry. About the ink. I guess I will erase it to be. Okay. So second bound is also easy. It says your make span is at least the largest processing time of any single job, max of PJ. Okay, why? Oh, that's one is easy, right? Because for the largest job, you have to do it on some machine. Now, no matter which machine you put this largest job on, that machine's load will not be less than that maximum time, right? Okay. So these two, now I'm going to bother you again. Are these two limit or lower bound clear? Yes or no? For optimal solution, the best solution, it cannot be better than either the first one or the second one. Is it okay? Yeah, I could understand that some of you still have difficulty, but the majority is fine. Okay. All right, then I will stop the. Right. Okay, so let's assume they are fine. Okay, let's assume they are fine. These two are fine. Then how do we prove? Okay, so we will do some trick here. What's the trick? We are taking out one job from our algorithm. Okay. So, for example, this one, right? So the machine with the maximum load, this job must be the last job added in. Okay. Why? Oh, sorry. Not this. Okay. So let's look at the machine with the largest load, and then we consider the last job added to this machine. So this largest job, at the time when it is added, we know that that machine should be smallest load, right? So at this time, second machine should be the smallest load before you add this job. Because our algorithm says add the job to the machine with the smallest load, right? Okay, so then what's the benefit of this observation? Well, the benefit is now we consider the load of machine I minus PJ, or I will do minus this PJ, okay? Then what's your conclusion? The conclusion is this value is at most the average workload of all the jobs. Is that right? So, because you see, at this time point, every machine has something to do, right? No machine is empty. No machine has already finishing all the jobs allocated to him. So at this point, you see the area of all the jobs, right? These things. They must be smaller than the total workload, right? Smaller than the total processing time. So if you multiply M on top of this time, it will be less than the total processing time, right? So this time is less than, you take all the processing time, divide by M. This must be true. All right. So this is one bound, right? And then we try to write this final make span in two parts. One part is Li minus Pj. The other part is Pj. Okay. We know Li minus Pj is at most this one, right? Okay. And then Pj is at most maximum of Pj, right? Okay. And then we know this is at most OPT. And this is also at most OPT. And that will give you 2 times the optimal make span. So you should ask, is the right side able to further minus Pj? Which part are you talking about? Right side. You mean, oh, you mean this minus Pj? No, you cannot do it. Yeah, you cannot do it because, you know, we are talking about the largest load here, right? The largest load, you can never argue every machine has something to do at that time. If you can argue every machine has something to do at that time, of course you can minus Pj here. But you see, there are a lot of gaps, right? There are many machines who are idle after some time, right? Before you talk about this time, right? So you cannot minus Pj. That does not hold. So is it clear? So it is okay. Oh, maybe. Okay. Well, so the reason we take this job off is to use the property applied by the algorithm, right? You always assign the job with the least load to the machine with the least load, right? If you do not use that one, you cannot have this bound like this. Okay. Yeah. Well, anyway, so this shows that, well, this greedy algorithm is a too competitive algorithm, right? Okay. So now we have one bound. All right. You see that when M is 2, then that means it's a 3/2 approximation or 3/2 competitive algorithm. And then we try to show nothing can do better than 3/2 competitive for 2 machines. Now again, it will be a good time to review how to design bad examples. Okay, so let's see how to design bad examples. Now suppose I give you 2 jobs. All right, both jobs are unit size, Pj equals 1. Okay, and then you have 2 choices to do the 2 jobs. Which 2 choices? Actually, there are many choices, not 2, but the 2 equivalent choices. So 2 principally different choices. Okay, there are some choices which are basically the same, but there are some choices which are different. So what are the 2 choices? Okay, so Sri said act 1, act 2. Okay, so 1 is I do the first job on machine 1. I do the second job on machine 2, right? This is one choice. The other is I put them both on one machine, right? Is it okay? All right. And then let's see what our adversary will do. It says, okay, because these are the two cases, right? One is put them together, right? The other is separate them. So if I put them together, what will the adversary do? Can anyone tell me? If the algorithm put the, okay. Remember, adversary is trying to release more jobs, right? So Ian, you are right, okay? So if you put them together on one machine, the adversary is very happy. He says, okay, now I will tell you, I will not give you any more jobs, right? Because in this case, I do not give you any more jobs, and then optimal will be evenly allocate them to 2 machines. But the algorithm, your cost is 2, right? Your processing time is 2, right? Okay. Okay. So this is one thing, right? So when you when the algorithm allocate 2 jobs on one machine, the adversary says, done, no more jobs. And then your algorithm suffer 2, but optimal should be this one, right? Optimal should evenly allocate them to 2 machines, right? Okay, now how about the second case? If the second case, if I evenly allocate 2 jobs to 2 machines, then what will the algorithm do? Or what will the adversary do? Okay, the adversary says, add a job, a big job, okay? I give a big job, okay? That's right. So instance B, I give it a big job, okay? If I give a big job, so actually, one thing, okay? If I give you a big job, it cannot be too big. If it's too big, then it's not too bad, right? You need to make the big job not too big, all right? So I hope you know what I mean by not too big, because if you, for example, the job is infinity, and then actually this solution is not too bad. It's just infinity plus 1, right? It's not bad. You have to exactly make the job of 2 unit lengths, right? Very good, okay? So that will give you the worst ratio, right? Okay, right? Because in this case, if this 2, this is 1, then the optimal solution is put these 2 jobs on one machine and put the 2 job on this machine. And then the make span is 2. But you are doing what? 3, 1 plus 2, right? This is 3 unit load, okay? So algorithm 3, but optimal is 2. So in both cases, the ratio is larger than or equal to 1.5. So in other words, nobody can do better than 1.5, but actually this 1.5 can already be achieved by the greedy algorithm, right? Okay. Okay, well, so I would like to see whether it's okay for the lower bound, okay? So why nobody can do better than 1.5 approximation? Oh, competitive. Okay, so it's nice to see that the number of students who didn't get it is less than the number of students who didn't get the earlier things, okay? That's very nice, okay? Well, but still, if you did not manage to understand this part, then, well, probably you need to spend a bit more time after the class. So basically, again, let me repeat, all right? The lower bound, or nobody can do better than something, will be proved in the following way, okay? So firstly, you will construct some example with some inputs already, all right? So this is designed by yourself. And then say, okay, I give you this input. What will your algorithm do? And then here we are listing all the possible things the algorithm can do, right? So we either allocate both jobs on onto the same machine, or we split them into 2 machines, right? We are doing everything possible. And then for each case, the adversary or the bad guy says, okay, if you do this, then I do something which make your performance bad, okay? I make you regret your earlier decision, all right? So in this case, we are saying, okay, how about I do not release anything, then then you cannot, you will regret your decision. You should have allocated them evenly to 2 machines, right? And then if you allocate them evenly to 2 machines, I will let you regret your decision because I give you a big job, which should be allocated to 1 machine exclusively and putting the 2 small jobs together on the other machine, right? Okay. So basically, the action the adversary do will make the algorithm decision or will make the algorithm regret about what he has decided earlier. All right. Okay. So Jiang Huan is asking why 2 minus 1 over m competitive. This is proved in the previous slide about upper bound. So I guess I will not go back for now. All right. Okay. So it's in the previous one. The upper bound is already proved in the previous slide. Okay. Yeah. So I will not elaborate on that. Maybe after the session. Okay. Okay. Now, now we come to some very interesting, and also some of you may have known the problems. The problem is about stochastic decision. Okay, it seems very difficult because it has some probability in it, but actually, well, it's still within some possible zone of understanding. Okay. Well, I personally do not like probability, but for this part, I'm still comfortable. All right. Okay. So we start with the so-called secretary problem. What is secretary problem? Again, it's very easy. You are choosing 1 candidate out of n rankable candidates who arrive online. Okay. So basically, you have a job position. You say, okay, please apply. Right. And then you see applicant after applicant. And then you will interview them and decide whether to give them an offer or not. Okay, but you can only give 1 offer. And your target is to give the offer to the best candidate. But you don't know who is best unless you see all of them. But remember, you need to make decision whenever you interview 1 candidate, right? You interview this candidate. After interviewing, you are able to compare this candidate with earlier candidates. And then you say, okay, I decide to give you an offer. But you cannot say, after I see better candidates later on, I revoke your offer. Well, that's not allowed, all right? Okay, so it's just like this, right? 1 by 1 coming in, you interview and decide whether you give him offer or not. Okay, and then the adversary. Well, the adversary here need to be limited in their power. Okay, so for example, in our model, we assume that you know n, you know how many applicants you will have. Okay, if you do not know it, then it's very natural. After you make a decision, say, oh, I want this candidate. And then the adversary will give you a lot more better and better candidates to make you regret, right? So basically that's not possible. If you do not know n, there's no way to have a good algorithm. Now, another assumption is the order is random, okay? The candidates come in random. Now, the reason is if the adversary can control the order, then he will put the best one at the beginning, okay? He will put the best candidate in the beginning. You interview this best candidate, you say, maybe there are some future better candidates, okay? Maybe I just give up this one. And then you will regret because, well, there are no better candidates later on, right? So if the adversary is less powerful, again, the probability of choosing the first candidate is also very, very tiny, right? Choosing the best candidate is still very tiny. So actually, this problem is very useful in practice, right? And not only job interview, you may also about your decision making, right? For example, you have some job offers, right? You get the offer from this company, and then it asks you, would you accept the offer? You say, maybe let me think, let me compare a bit more. But he has some deadline, right? He said, okay, please tell us within 1 week. Now, by that time, you don't have any other offers. So you may say, maybe there are some better one later on. Maybe I just give it up. Then you may regret, okay, after I give it up, maybe there are no better offers later on. Then I will feel very sorry, right? So secretary problem tells you, well, there is a best strategy where the probability of choosing the best candidate is quite big. Okay, well, so now, just again, as usual, let me bother you again about the question, okay? So are you clear about the target and the setting of the problem? You try to select the best candidate, okay? Ah, good, very nice, okay? Not a single negative, very nice. Okay, so now let's see how to do this problem. So now, as I said, right? If the adversary is too powerful, then you cannot have any bounded competitive ratio. So now let's see. Less powerful adversary allows you to know n beforehand. You know how many candidates. And also, the candidates will arrive in a uniformly random distribution. In other words, any permutation of the candidate is possible to appear, has equal probability to appear to you. Okay, like if you have 3 candidates, then 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. All of them are possible with equal probability. Okay, so now let's see the optimal offline algorithm. We try to compare, right? So optimal offline algorithm is I just check all their performance, right? I pick the best one. Okay, so you see, optimal offline algorithm can always choose the best one with probability 1, right? No uncertainty. Okay, so we are trying to maximize the probability that we choose the best candidate, right? Okay, now there are some strategies, very straightforward. The first one is I take the first candidate. Now, what's the probability I successfully get the best candidate? Given that all the permutation is possible. Oh, very good. Okay, it's 1 over n, right? Okay, because the first one has the best one can appear in any position with same probability, right? You have n positions, so with probability 1 over n, it will appear in position 1, right? And then you got it, right? By choosing the first candidate. Okay, good. So this one is very easy to analyze. How about the next one? Strategy 2. So, okay, I interview the first half candidates. I do not select any one of them. Okay, now here comes half n, right? And then I say, okay, for the next half, I select the first one, which is better than all the first half n candidates. Okay, so you see, 4 people, I check the first 2, okay, but I do not give them offer. And then I check the last 2. I give the offer to the first one, which is better than both of them, right? Okay, so this one is a bit hard to analyze, but still manageable. Why? Because finding the best candidate using this algorithm, it can be broken down to the product of 2 probability. In order for you to choose the best one in the second half, it means that, yeah, that means got information from first half. Yeah, okay. It means that the best one in the second half, right? This is the first probability, right? The best one must be in the second half. There's another event that must happen in order for you to succeed. That event is the second best is in the first half. Okay? Why? Well, if the second best is in the second half, then it's possible you select the second best because it can be better than anyone in the first half, right? Okay, so these 2 probabilities, right? The first one is the best one is in second half. The second event is the second best is in the first half, so that when you check the second half, the guy who is better than the first half must be the best one, right? Okay, so that will make the whole probability work. So that gives you half-half, right? Anyone, any candidate appearing in any half, the probability is half. So these 2, each of them will be half. So multiply together, it's a quarter. So that means you have quarter chance of selecting the best candidate. Okay. Yeah, you are allowed not to hire anyone. Yes, you're right. If the yeah, Xinran asked, is probability finding best candidate equal to half? Well, actually, it's not, because yeah. So as I said, right, if you have a sequence of people, if 1 is here, 2 is here, something like 3, 4, 5, 7. Okay. Now you check in this order, and then you pick the first half, and then in the next half, the first one who is better than all of them is 2. So in this case, actually it didn't manage to pick 1. Okay. So the probability is not half. Yeah. Okay. Okay. So it's very interesting thinking exercise, all right, about probability. I know that some of you may not get it, but well, it's fine. You may take some time to think about it. Okay. Well, very good. Haifeng asked, what if n is odd? Wow, that's a tough question. Okay. Well, you may do some minor adjustment of probability. It will not be too far away from a quarter. But anyway, you have to decide where the middle guy will go, right? Okay. Yeah, it's a very good question. In reality, you need to handle those special cases, right? So if not even, then the algorithm will break, and then probably you will need to take a floor function, something like this, right? Seating here. Okay. Well. Okay. Oh, okay. You should ask a target. Okay. Target is to find the it's to maximize the probability of selecting the best one. Okay. Not the best possible score. They are different. Okay. So there are also some other objectives, like I want to maximize the expected quality of candidate I selected. But here, this is not a target. Our target is to select best one. The probability of selecting the best one. Yeah, so Jinpeng asked, how about if the second best is not in the first half, but the best happened to be in the first half? Yeah, and then okay, so you mean this, right? You mean something like this, right? Like this. So 1 is the first in the second half. Now, in this case, you can't select him, right? In this kind of sequence, you manage to select the top one, right? Top one. Okay, so again, yeah, very good. Thank you for answering for me. Well, so about half and a quarter, well, of course, there are some details that need to be figured out. But again, it's not exactly half. It does not mean that 1 before 2, 1 is already selected. It's not true. If 1 before 2, 1 is already selected, then it's okay. But then if it's not the case, then it will not be half. All right. So it's not that that easy to derive the probability. Okay. So I guess today I'm just stopping at the optimal strategy. All right. The detailed analysis I will postpone it to next week. Now, actually, half is not the best. The best one is interview the first N/E candidates, but do not select. So this E is 2.73 something. So that's a natural number, right? Okay. And then for the others, select the first one that is better than all the first N/E candidates. And doing this will give you a success probability of 1/E. So 1/E is better than 1/4. Okay, because E is less than 3. All right. Yeah, okay, so I guess I will stop here. The remaining process, oh yeah. So yes, indeed, we need a floor ceiling, definitely. Wenchong, you're right. Okay, I'm just being lazy here. All right, do not put any floor ceiling here. All right, we assume that the N/E is when N is super large, and also these numbers are negligible, so that analysis will go through. Okay, but in reality, we definitely need to add a floor ceiling. Okay. Yeah, so the analysis will be next time. And meanwhile, during this week, please figure out, or please make sure that you understand this part. All right, why this probability is equal to this times this. All right, and also for the earlier topics, you can think about why certain lower bounds look like that, why certain algorithm, its performance is good. All right, okay. And then next week we'll come to the last part of the algorithm topic. Yeah, so the last part usually will not go deeper into those topics because those will be more advanced things. So in this course, those advanced things will only need a moderate level of understanding, not full level. Okay. Oh, sorry. Next week, no, next week means next academic week, which is 2 weeks later. Okay. Thank you for reminding me. All right. Next week we don't have lecture because of Chinese New Year. Yeah, happy Chinese New Year. Several days earlier. Our next week will be February 9 or something. Yeah, I forgot the date. Yeah. Anyway, it's 2 weeks later. Two physical weeks later. Yeah. Oh, February 10th. Thank you. Okay. Yeah, so I hope that you will feel today's topic to be slightly easier than last week's topic. Yeah, because I believe that approximation algorithm will be more challenging than online. That's for sure. Okay. Yeah, thank you. So I hope that you'll feel happy. All right, but online is very useful. You see that by knowing some basic techniques, you can do a lot of things actually. Yeah. Okay. Yeah, feel free to ask some questions, to stay behind, ask some questions. I will stay around until 3. Yeah. Yeah. Happy holidays. Okay. And actually, some of you are raising very good questions. One is, do we have exercise for this week? The answer is no. Your exercise is to figure out or fully understand those, or not fully, okay, 90% level understanding the examples we talk about in this lecture and also previous ones. And then about the learning materials, I will try to post some on Canvas about approximation algorithm, online algorithm. So actually, approximation algorithms, there are some textbooks called approximation algorithm. So there are some. So there's one book called Approximation Algorithms, written by Vazirani. But that book, every chapter is very short. It might not be easy to comprehend, okay, as a beginner. So let me just post some learning materials online on Canvas after I find someone. Yeah. So Jinpeng, what are you asking? Will QE what? Oh, you mean will QE test you on online or approximation? So actually, how to say? So for QE, the main focus will be the basic algorithms like greedy, dynamic programming, divide and conquer, etc. But remember that in approximation algorithm and online algorithm, we also have greedy. We also have DP. So basically, we will test you. It's possible to test you on greedy or DP with their applications. Okay. So we do not exclude the testing on online or approximation, but we will limit them to the basic understanding. At least if I test you on online algorithm, I will give you definitions. I will, well, okay, to be fair to all the students, right? So I will give you definitions, and you need to think about, you need to, figure out the solution by yourself, but you do not need to worry about those basic, yeah, as I said, do not need to worry about memorizing the definitions. That's not needed. Yeah. Yeah, and then, okay, thank you. And then also for in-class exercise, yes, there are 2 pieces now, all right? one easy question, and then a tutorial question set, right? So you will upload them when you see the submission open for submission. Oh, so the Canvas assignment is open for submission, then you can submit them. Okay, so basically we will probably have one more piece of in-class exercise before the midterm. Yeah. Okay. And also the assignment will be released after next lecture. Yeah, tutorial only has tutorial 1. Okay, Canvas only has tutorial 1. You're right. Tutorial is not every week. Okay, we will provide some assignment. Yeah, after we finish all the algorithm part. Our mark distribution is 5% for each half. All right, total is 10%. So you may consider that as some kind of a attendance with your initial thought. Okay. Oh, you mean within the 3 pieces? Oh, okay. You mean this? Oh, there's no certain distribution. Okay. As I said, what I would like you to do is just giving some sensible ideas. Now, at least for the first question, you need to be correct. Okay. For tutorial 1 set, you just need to provide sensible solutions. And then for the last one, the third one, similar, maybe similar, maybe similar as the first question, or similar as the tutorial 1 set. Okay, but they have no firm distribution. Okay, each question carries similar weight in the whole 5%. As I said, this is mainly for attendance purpose. All right. Okay. Yeah. Any other questions? Okay. PPT 30 E by dividing. Let me see. So Xinan, you're asking PPT 30 or 33? I think it's 33. If you divide using E, then the probability of finding the best is 1 over E. Yeah. So if you mean this, then yes. Oh, okay. Well, wait for a moment. E is not any number. Okay, this E is a natural number. Yeah, it's a natural number. Yeah, thank you for answering the question for me. And someone asked a bit confused about the piece. What does piece mean? That's actually earlier when I talk about in-class exercise. One student asked, what's the percentage of or distribution of different components, like a first question, tutorial 1 questions, and the third piece. Okay, so they're asking about how many points will go to each piece. 1, 2, 3 batch. Okay, so I mean that the free batch will bear similar percentage of points. For example, I cannot give you example now because so according to what I designed, the 3 things add together will be around 6 or 7 questions. So basically, the marking is not trying to differentiate using that. Okay, I believe that for example, for the first question, is everyone can do it. Okay, so basically everyone will get points. So this 10% in class, I think that majority of you will get 10%. So that part is not the major assessment. Okay, that's something which serves as a foundation. All right, and then built upon that will be assignment and midterm, which will mainly affect your coursework. Okay. Yeah. So, any other questions? Okay. So if no questions, then see you in 2 weeks. Have a nice holiday. Oh, okay. One last question I answer. It would be nice if we have more easy bonus question. Okay. Well, bonus is a bonus, right? It's extra. So of course, sometimes you will have easy bonus, but sometimes not. Okay. For example, today I only give, say, 6 bonus points. Okay. So, well, yeah, it depends on the topic, right? Okay. Yeah, I also hope to give easy bonus. But again, it depends. Also depends on your performance in midterm, right? Okay. Okay. Yeah. Then enjoy your holiday. See you in 2 weeks. Yeah. See you. Thank you.